Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're settling into one of the strangest little puzzles in modern physics, a puzzle with a name so ordinary that it almost feels misleading. Spin. It sounds simple at first, almost familiar. A spinning top, a bicycle wheel, a planet turning through the dark, a coin wobbling on a table before it finally gives into gravity. We know what spinning looks like in everyday life. Something turns around an axis. Something has a surface that moves, a shape that rotates, a before and an after that we can follow with our eyes. But in the tiny world of particles, things are not so comfortable. Electrons are said to have spin, and yet they are not little balls rotating like planets. Quarks have spin, photons have spin, atoms build their behaviour from spin, magnets owe much of their character to spin, and yet the word itself is not quite what it seems. So tonight we're going to walk gently into that confusion, not to rush through it, not to flatten it into a quick definition, and not to pretend that quantum physics is less strange than it is. We're going to let the strangeness breathe a little. Because sometimes the most useful way to understand a deep idea is not to attack it directly, but to circle around it slowly, the way you might walk around an old clock in a quiet museum, noticing the gears, the brass, the scratches, and the soft, stubborn rhythm that has somehow kept going for years. Before we begin, I would love to know where in the world you're listening from tonight. Are you tucked away in a quiet room after a long day, maybe with the lights low and the world outside turning slower than usual? Are you listening in the morning, with sleep still clinging to the edges of your thoughts? Or are you somewhere in the middle of the night, in that peculiar hour when the house seems to have its own kind of silence? And if you feel like sharing, what is around you right now? A cup of tea, a window, a restless cat, a blanket that has become far more important than expected? It is a fitting question for a subject like this, because spin is one of those hidden properties that helps make ordinary things ordinary. It is in the magnets on your fridge, the electronics near your bed, the chemistry in your body, and the matter beneath your hand. Quietly present, almost never noticed. If this little journey helps you relax, gives your mind something calm and curious to follow, or simply keeps you company as you drift towards sleep, I would be grateful if you gave the video a like and subscribed. It helps this peaceful corner of science reach others who may also enjoy learning without being hurried. And if you are already settled in, there is no need to sit up straighter or prepare like you're about to take an exam. Quantum physics has a reputation for being sharp and difficult, but tonight we can approach it gently. No blackboard, no frantic chalk, no need to solve anything. Just a slow exploration of why particles can have something called spin, even when nothing is physically spinning in the way our everyday senses expect. The first thing to notice is that language often lags behind discovery. Scientists name things before they fully understand them. Sometimes a name begins as a useful guess, a helpful image, or a rough comparison, and then later the universe turns out to be stranger than the image allowed. Spin is one of those names. When physicists first began to uncover this property, they reached for a familiar word because the behaviour reminded them of rotation. Particles seemed to carry a kind of built-in angular character. They acted as if they had a tiny internal twist. They contributed to magnetism in ways that looked related to spinning electric charge. The word spin was convenient. It gave the mind something to hold. But convenience is not the same as literal truth. An electron is not a miniature Earth turning through space. It does not have little continents sliding around a tiny equator. It does not have a painted dot on its surface that comes back into view after every rotation. As far as our best experiments can tell, an electron behaves like a point-like object. That does not mean it is a tiny hard dot in the way a grain of dust is a tiny hard thing. It means that when we probe it, we do not find an extended surface with parts arranged across a volume. If there is no surface, there is nothing in the normal sense to rotate, and yet the electron has spin. That is where the puzzle begins. If particles do not spin, why do they have spin? This is one of those questions that sounds like it should have a neat answer, as if physics might say, "Ah yes, it is simply this." But the truth is more interesting. Spin is not a mechanical rotation, it is an intrinsic property. Intrinsic is a quiet but important word. It means the particle has it as part of what it is, not because it is doing some extra motion in the background. An electron has an electric charge, it has mass, it has spin. These are not decorations added on later, they are part of the identity of the particle. Asking why an electron has spin is a little like asking why it has charge. At some point, physics describes what the particle is and how it behaves, and spin is one of the central features in that description. Still, that does not mean we are left with a label and nothing more. Spin has consequences. It changes how particles respond to magnetic fields. It helps decide how atoms arrange their electrons. It plays a role in why matter has structure, why chemistry works as it does, why some materials become magnets, and why certain technologies can exist at all. Spin is not a metaphor that physicists keep around out of sentiment. It is measurable, it is reliable. It is woven into the rules that allow the world to have form. Imagine for a moment that you're sorting a drawer full of objects in dim light. You cannot see every detail clearly, but you discover that some objects behave differently when you bring a magnet near them. Some line up in one way, some in another. Some refuse to share the same condition as others. Some pair off neatly, while others leave an unpaired character that changes the whole personality of the material. You might not know what each object looks like inside, but you would know there is a hidden property sorting them into patterns. Spin is like that. It is not something we see by watching a particle twirl. It is something we infer from what particles do, from the marks they leave on experiments, from the structure they force nature to build. One of the great lessons of quantum physics is that the microscopic world does not have to imitate the familiar world. This can be uncomfortable at first. We naturally want small things to be like large things, just reduced in size. A dust grain is like a pebble, only smaller. A pebble is like a boulder, only smaller. So perhaps an electron, we imagine, is like a little bead, only far smaller. But quantum objects are not simply smaller versions of classical objects. They're governed by rules that do not fit neatly into everyday pictures. They can behave like waves in some situations, and like particles in others. They can exist in states that only become definite when measured. They can be linked across distance in ways that seem to ignore our ordinary sense of separation. And they can have spin without literally spinning. This does not make spin unreal. It makes it quantum. A familiar word has been attached to an unfamiliar kind of property. That is partly why it causes so much confusion. The word invites us to imagine a tiny rotating object, then the science quietly takes that image away. It is rather like being told that a particle has flavour, only to learn that nobody expects a quark to taste faintly of lemon. Physics sometimes uses ordinary words in technical ways. Spin is one of the most famous examples. The word survived because it points to certain mathematical and physical similarities with rotation. But if we take it too literally, it leads us into trouble. There is a gentle irony here. Spin is one of the reasons the world is stable enough for us to ask questions about spin. Without the quantum rules connected to spin, electrons would not arrange themselves around atoms in the same layered way. Matter would not have the same richness. Chemistry would be unrecognizable. The chair beneath you, the blanket over you, the muscles that let your eyes grow heavy, the quiet electrical signaling in your brain as you listen, all of it depends on quantum properties that have no simple everyday picture. The ordinary world is built from things that are not ordinary at all. This is one of the reasons quantum physics can feel both unsettling and comforting. Unsettling, because it tells us that our intuitions are not the final measure of reality. Comforting because the strangeness is not chaos. It has rules. It has patterns. It makes predictions that have been tested with extraordinary precision. The microscopic world may not match our first images of it, but it is not random nonsense. It is more like a language we did not grow up speaking. At first it sounds strange. Then slowly, certain phrases become familiar. Spin is one of those phrases. To understand why the word appeared, we need to place ourselves in the early days of atomic physics, when scientists were trying to explain why atoms gave off light in specific colours, why magnets behaved as they did, and why electrons did not simply collapse into the atomic nucleus. The atom was no longer a vague idea. It had become a laboratory reality. Spectra, those coloured fingerprints of elements, revealed that electrons could occupy only certain states. Nature seemed to be counting, but not in the smooth, continuous way classical physics expected. It preferred steps, levels, allowed patterns. The world was becoming quantum one experiment at a time. As researchers studied these patterns, they found that the existing labels were not enough. Electrons in atoms needed another property to explain their behaviour. Something about them came in two possibilities when measured along a chosen direction. Not because the electron was literally a little arrow already pointing one way or the other in ordinary space, but because the quantum state produced these distinct outcomes. It was as if nature allowed the electron to answer a certain question in only two ways. This was not what classical physics had trained people to expect. A spinning object in everyday life can be tilted at any angle, a small top can lean this way or that, this. But the electron, when asked the right experimental question, gave discrete answers. That discreteness is one of the signatures of quantum mechanics. The world at small scales often refuses to vary smoothly. Energy levels, measurement outcomes, angular properties, many of them arrive in permitted values rather than every imaginable value. Spin belongs to this family of quantum behaviour. It is not a hidden little wheel turning inside the particle. It is a built-in way the particle transforms, responds, and contributes to the larger patterns of matter. A useful first step is to loosen the grip of the everyday picture. We can keep the word spin because physics uses it and because it does point towards something related to angular behaviour. But we do not need to imagine a tiny rotating sphere. Instead, think of spin as a kind of internal orientation that has no perfect classical counterpart. That phrase is not meant to be mysterious for its own sake. It is an honest admission that the familiar world does not provide an exact image. We can describe spin through what it does, we can measure it, we can use it, we can build machines that depend on it, but we should not force it into the shape of a toy top just because the word tempts us. This is a common moment in science, the moment when a metaphor has done all it can do and must be set down gently. The metaphor helps us enter the room, but it cannot show us everything inside. At first, spin sounds like rotation. Then we learn it is not ordinary rotation. Then we begin to see that it is something deeper, a property tied to symmetry, measurement, magnetism, and the identity of particles themselves. That deeper view is less visual, but it is more accurate, and yet it is worth being patient with the visual imagination. We are visual creatures. We understand by picturing. We like wheels, waves, arrows, curves, and little moving parts. There is nothing wrong with that. Many great discoveries began with images, but quantum physics often asks us to use images lightly. Hold them like a candle, not like a cage. Let them illuminate what they can, then let the darkness remain where the image no longer reaches. In the case of spin, the candle shows us that the particle has a kind of angular character. It interacts with magnetic fields, it combines with other spins, it affects how particles can share states, it helps organise matter. But the candle goes out when we try to picture the particle as a small rotating ball. If an electron were literally spinning fast enough to account for its magnetic behaviour, the surface would have to move in a way that conflicts with relativity. And if the electron has no known surface or size in the classical sense, the picture becomes even less useful. So we stop treating spin as a tiny rotation and begin treating it as its own quantum property. This can feel like a loss, but it is also an opening. Once we stop demanding that particles behave like small planets, we can start asking better questions. Not what is the electron made of in a mechanical picture, but how does the electron behave under the rules of the quantum world? Not what little parts are turning, but what measurements are possible, what patterns appear, what symmetries are respected, and what effects show up in atoms and materials. Spin becomes less like a hidden motion, and more like a key to a deeper grammar. That deeper grammar is everywhere. It is in the way electrons fill atomic shells, giving elements their personalities. It is in the way two electrons can pair in a chemical bond. It is in the reason some materials are magnetic and others are not. It is in the operation of magnetic resonance imaging, where nuclei inside the body respond to magnetic fields and help create pictures that doctors can use. It is in the ambitions of quantum computing, where spin can be one candidate for storing delicate quantum information. It is also in the behavior of light, where photons carry their own form of spin and help explain polarization. A word that began as a slightly misleading analogy has become one of the central tools for describing reality. So tonight, as we begin this slow journey, we will not try to make spin less strange than it is. We will make it less lonely. We will connect it to experiments, to atoms, to magnets, to the stability of matter, to the surprising fact that some quantum objects need a full turn and then another full turn before they return to their starting behavior. We will let the idea build gradually, not as a trick, but as a way of seeing how nature can be precise without being easy to picture. For now, the important thing is simple enough to rest with. Particles have spin, but they are not spinning like tiny planets. Spin is an intrinsic quantum property, one that behaves in some ways like angular momentum, but does not come from ordinary rotation. The name is historical, the effect is real, and the consequences are enormous. It is one of those places where the universe says, quite calmly, that it is under no obligation to match the images we first bring to it, and perhaps that is a soothing thought in its own way. The world does not need to be fully pictured to be understood. Some truths arrive not as neat mental photographs, but as reliable patterns, patient measurements, and careful words. Spin is one of those truths. It sits quietly inside the particles that make up matter, giving structure to atoms and personality to materials, while refusing to become a little spinning bead for our convenience. The universe is not being difficult. It is simply being itself. So settle in a little more. Let the day loosen its grip. Somewhere in the quiet machinery of the room around you, electrons are arranging themselves according to rules that no human eye can see directly. Magnets hold to surfaces. Circuits wait in their dark plastic shells. Atoms keep their shapes. Your body keeps its chemistry. And beneath it all, this strange property called spin is doing its work without fuss, without noise, and without anything needing to whirl like a toy top. To see how physicists first realized that particles carried this hidden kind of twist, we need to move into the early experiments where beams of atoms, magnetic fields, and a few unexpected marks on a detector began to show that the small world had more structure than anyone had imagined. That first experimental trail is worth following slowly, because the word spin can be one of the most persistent little traps in all of physics. It sounds so clear that it nearly explains itself before we have even begun. A spinning coin on a table, a skater drawing in their arms, a wheel turning in the rain, the Earth making its patient daily rotation. These are all familiar things. They have shape, they have parts. One side moves here, another side moves there, and after enough turning, the object returns to something like its earlier position. If you painted a tiny mark on a ball and spun it, you could watch the mark go around. That is the ordinary picture the word spin quietly places in the mind. It is simple, useful, and completely understandable. It is also not what an electron is doing. The trouble begins because physics often borrows everyday words and then asks them to carry meanings they were never built to carry. Charge does not mean a particle is being asked to pay for something. Colour in the world of quarks does not mean tiny bits of matter are painted red, green, or blue. Flavour does not mean they taste like anything, which is probably for the best because nobody needs a spoonful of strange quark before bed. In the same way, spin does not mean that the particle is a tiny marble rotating in space. The word was chosen because the property behaves in some ways like rotational motion. It contributes a kind of angular character. It gives particles magnetic behavior. It affects how particles combine and arrange themselves. But the more carefully physicists looked, the clearer it became that spin could not be explained as ordinary turning. Let us begin with the most natural picture and let it fail gently. Suppose an electron really were a tiny ball of electric charge spinning around. If electric charge moved in a circle, it would create magnetism, a little like a loop of current. That sounds promising at first, because electrons do behave as if they carry a small magnetic character. Place them in a magnetic field and they respond. In atoms, this response helps shape the pattern seen in light. In materials, the collective behavior of many electron spins helps create magnetism. So a tiny spinning charged ball feels like a reasonable first idea. It gives the mind something mechanical to imagine. It lets us say perhaps the electron is like a little planet, turning with charge smeared across its surface. But then the idea begins to creak. If the electron were a literal rotating ball, it would need some size. It would need an outside edge, or at least an extended structure with different parts at different places. Yet every experiment that probes the electron at smaller and smaller scales finds no evidence of a little surface, no tiny crust, no internal geography, no visible diameter in the ordinary sense. The electron behaves, as far as our current experiments can tell, like an elementary point-like object. Point-like does not mean we can picture it as a hard little dot with a polished surface. It means that when experiments ask whether it has an extended structure, the answer keeps coming back no, not in any way we can detect. And if there is no surface, there is no ordinary thing to spin. Even if we tried to keep the picture alive, another problem appears. To account for the electron magnetic behavior using literal spinning, the imagined surface would have to move absurdly fast. In some simple versions of the old picture, parts of the electron would need to move faster than light. That is not allowed in relativity. Nature does not permit matter or information to outrun light through space. So the little spinning ball picture does not merely become awkward. It breaks one of the most deeply tested rules of modern physics. It is a charming picture, but it cannot be the truth. There is another clue, quieter, but just as important. A normal spinning object can spin faster or slower. It can have a range of speeds. A top can wobble. A planet can rotate once in many hours or once in many days. A wheel can slow down gradually. Ordinary rotation is smooth and adjustable. But the spin of an elementary particle is not like that. An electron does not have a spin that can be sped up by giving it a little push, as though we were flicking a toy top. You cannot take an electron and make its intrinsic spin larger or smaller. Its spin is fixed as part of what kind of particle it is. Every electron has the same kind of spin. Every electron carries that property in the same amount. It is not an activity the electron happens to be performing. It is a built-in feature of its identity. This distinction is important enough to rest on for a moment. In everyday life, spinning is something an object does. A football spins because someone threw it in a certain way. A washing machine drum spins because a motor turns it. A planet spins because of the history of the cloud of matter from which it formed. These are motions. They can change. They can speed up, slow down, tilt, stop, or be disturbed. But a particle spin is not like a mood, a habit, or a motion it picked up somewhere. It is more like charge or mass. It belongs to the particle. It is there even when the particle is not orbiting anything, not moving through a laboratory in any dramatic way, not behaving like a little wheel. Spin is not added to the particle. It comes with the particle. This is why physicists call spin intrinsic. The word intrinsic simply means that the property is part of the thing itself. A particle may move through space, and that motion can give it ordinary angular momentum if it travels around something. An electron in an atom can have orbital behavior, a kind of quantum version of angular arrangement around the nucleus. But spin is separate from that. It does not depend on the particle tracing a path around a center. It does not require the particle to be moving in a circle. It is present even for a lone electron drifting without any tiny orbit to perform. The name spin survived because the property shares some family resemblance with rotation. It is connected to angular momentum, which is the physics idea associated with turning motion. It responds to rotations in space in a specific way. It produces magnetic effects that resemble what moving charge could produce. It combines with other angular properties according to careful rules. In that sense, spin is not a random name pulled from a hat. It points towards something real, but it points by analogy, not by literal description. The danger comes when we take the analogy too seriously and imagine a hidden miniature machine. A better way to approach spin is to think of it as a quantum label that tells us how a particle behaves when the universe asks certain questions about direction and rotation. That may sound less visual, but it is closer to the truth. In quantum physics, a particle is not fully described by where it is and how fast it is moving. It also has a state, a complete description of the possibilities it carries and how those possibilities may appear when measured. Spin is part of that state. It tells us, among other things, how the particle will respond when it passes through a magnetic field, how it can line up relative to that field, and how it may combine with other particles. Consider an electron moving through a device that creates an uneven magnetic field. If the electron were a tiny classical magnet that could point in any direction, you might expect a broad smear of possible deflections. Some would tilt a little upward, some a little downward, some somewhere in between, depending on how the tiny magnet happened to be oriented. But quantum particles do not always offer a smooth menu of possibilities. When a spin measurement is made along a chosen direction, the result comes in distinct outcomes. The electron is found in one of two possible responses for that measurement. It does not reveal itself as a tiny arrow that was quietly pointing at any angle beforehand in the ordinary way. It behaves according to the rules of quantum measurement, and those rules give definite results from a state that may have carried several possibilities before the measurement. This is one of the places where spin becomes difficult, because it asks us to separate measurement from imagination. We can say what the detector records. We can say how often certain results appear. We can predict how the particle will behave if we turn the measuring device. We can use the results to build technology, but we cannot honestly say that the electron was simply a tiny spinning ball with a known little axis waiting to be revealed. The experiments do not support that everyday picture. Quantum properties are not always hidden classical details waiting for better glasses. Sometimes the old categories themselves are the wrong categories. The word axis is another subtle trap. A spinning globe has an axis. The Earth has an axis. A wheel has an axle, or at least a line around which its motion is organised. But an elementary particle with spin does not need to contain a tiny physical axle. When we measure spin along a direction, we choose a direction in our experiment. The result tells us how the particle state answers that particular question. Choose a different direction, and the structure of the answers changes in a quantum way. This does not mean the particle had a little rod inside it pointing somewhere definite all along. It means the particle has a spin state, and that state relates to possible measurements in different directions. For a sleepy mind, this might sound like a complication, but it is also a relief. We do not have to make the electron into a tiny broken toy. We do not have to imagine it spinning faster than light or hiding a surface nobody can find. We can let go of the mechanical picture and allow spin to be what experiments say it is. A quantum property with rotational character, intrinsic to the particle, measurable through its effects, and not reducible to familiar turning motion. There is a useful comparison with temperature. One molecule of air does not have a temperature in quite the same way a whole room does. Temperature emerges from the motion of many particles together. The everyday word feels simple, because we experience it directly as warmth or cold, but underneath it lies a more careful description. Spin is almost the reverse situation. We borrowed a familiar word from everyday motion, but at the quantum level the property is not the everyday motion at all. It is fundamental in the particle description, and the familiar picture is the thing that must be corrected. Another comparison is personality, though of course particles do not have personalities in the human sense. Still, if you met two people wearing identical coats in dim light, you might not see every detail, but you could notice that one always answered a question in a particular way while the other answered differently. Over time, you would learn that there is something consistent about them. Spin is like that in experiments. It is recognized through behavior. The particle passes through a magnetic arrangement and leaves one kind of mark rather than another. Many particles together produce patterns in atoms and solids. Something consistent is being expressed. We name that consistency spin. The reason this matters is that spin is not a decorative detail. It is not a minor quirk that could be ignored if quantum physics had chosen a better word. It is one of the central facts that makes matter behave the way it does. Electrons have spin, and because of the rules attached to particles with electron-like spin, they cannot all pile into the same quantum condition. This leads to the structure of electron shells in atoms. Those shells shape chemistry. Chemistry shapes molecules, rocks, water, air, cells, bodies, and the quiet nervous system that may currently be deciding whether to keep listening or drift gently towards sleep. The fact that spin is not literal spinning does not make it less important. It makes its importance more surprising. This is one of the grand recurring themes of physics. Some of the most solid features of daily life are supported by things that cannot be pictured in a solid daily life way. A wooden table feels firm because of electrical forces and quantum rules between atoms. A magnet sticks to a fridge because of the collective alignment of quantum properties inside matter. Light fills a room because electromagnetic fields carry energy in a way that can also be described through photons. Familiar experience is the surface. Beneath it, nature is not made of little clockwork copies of familiar objects. It is made of fields, states, particles, probabilities, and symmetries. Spin belongs to that deeper layer. Symmetry is one of the quiet keys here, though we can speak of it without rushing into mathematics. In physics, symmetry means that something remains consistent when we change our viewpoint or perform a transformation. If you rotate a plane sphere, it looks the same. If you move an experiment from one place to another and the laws still work, that is a kind of symmetry. Spin is deeply connected to how particles behave under rotations. Not rotations of a tiny surface, but rotations of the coordinate system, the measuring arrangement, the way the state is viewed. Some particles return to the same kind of behavior after an ordinary full turn. Others, including electrons, have a stranger relationship with rotation, one that has no everyday object equivalent. Later, this will lead us to one of the oddest facts in quantum physics, the fact that certain spin states need a double turn before they fully come back to themselves. For now, it is enough to notice that spin is linked to the logic of rotation without being a little rotating body. That difference between rotating an object and transforming a quantum state is where many misunderstandings settle. If you rotate a mug on a table, the mug itself turns. Its handle moves from one side to another. If you rotate a measuring direction in a spin experiment, you're changing the question asked of the particle. The particle state has rules for how it responds to that change. Those rules are precise and have been tested again and again, but the response does not require a little mug-shaped electron with a handle swinging around inside it. The quantum state is not a tiny household object. It is its own kind of physical description. One might ask whether all this means spin is just mathematics and not really physical. That is a fair worry, but in physics the line between mathematical description and physical reality is not always separated by a neat fence. Spin has physical effects. It changes measurable outcomes. It gives particles magnetic moments. It influences the spectra of atoms, the structure of matter, the behavior of metals, the design of medical imaging machines, and the possible building blocks of quantum technologies. A property that changes what experiments record is not imaginary. It may be hard to picture, but it is not optional. Think of music on a vinyl record. If you had never heard sound before and only looked at the groove, you might not imagine a song. You would see a winding trace, a pattern of tiny changes. Yet with the right device, the pattern becomes audible. Spin is not exactly like a groove, but the comparison helps in one respect. A hidden structure can be real because of what it does when the right interaction reveals it. We do not see spin directly with our eyes, we see its consequences, just as much of science sees reality through consequences. We know air exists because leaves move and lungs fill. We know gravity acts because objects fall and planets orbit. We know spin exists because particles behave in ways that demand it. It is also important not to imagine that physicists are embarrassed by the word spin, as if everyone knows it is wrong but nobody has bothered to fix it. Scientific language carries history. Once a term becomes woven into experiments, textbooks, technologies, and conversations, it often remains, even when its meaning grows more subtle. The word atom originally meant something indivisible, yet atoms can be divided into nuclei and electrons, and nuclei into protons and neutrons, and those into quarks and gluons. The old word stayed, but the understanding changed. Spin is similar. The name came from an analogy, then the theory deepened. The word stayed because it is useful, and because everyone in the field knows how to handle it carefully. For someone meeting the idea for the first time, it may help to keep two thoughts side by side. First, spin is like rotation, in that it is connected to angular momentum and magnetic behaviour. Second, spin is not rotation in the ordinary sense, because elementary particles are not tiny extended objects turning around an axis. Both thoughts are needed. If we keep only the first, we imagine a little spinning ball and fall into trouble. If we keep only the second, the name spin seems arbitrary and confusing. Held together, they give a more honest picture. Spin is the quantum version of a rotational property, but not a classical spinning motion. This is why many explanations say that spin has no exact everyday analogy. That phrase can sound like a door closing, but it is not meant to shut us out. It is meant to protect us from a bad picture. A bad picture can be worse than no picture, because it quietly answers questions in the wrong way. If we imagine an electron as a tiny top, we may ask what surface is moving, what material it is made of, how fast its edge travels, and why it does not fly apart. Those are reasonable questions for a top. They are not the right questions for an electron. The better questions are how spin is measured, how spin states combine, how spin affects magnetic behaviour, why particles with certain spin obey certain rules, and how this property appears in the structure of matter. The shift can feel like moving from a children's picture book into a language lesson. At first, we miss the pictures, but then we begin to hear the grammar. Spin up and spin down are not little arrows painted on a bead, but possible outcomes of a measurement along a chosen direction. Pairing spins is not two tiny tops politely balancing each other on a shelf, but a rule about how quantum states combine. Magnetic materials are not merely filled with countless miniature planets all turning in the same direction, though that image has a small usefulness. They are systems where quantum spins and their interactions produce large-scale behaviour. The pictures soften, the rules sharpen, and understanding becomes less about seeing and more about recognising patterns. That is not a weakness of physics, it is part of its power. Human senses evolved to help us move through a world of stones, trees, water, animals, tools, faces, food, danger, and weather. They did not evolve to picture the quantum state of an electron. There is no reason to expect our imagination to come preloaded with the correct image for spin. The surprise is not that quantum physics is strange. The surprise is that careful experiment and patient reasoning can reveal it at all. So when we say that particles have spin, we're not sneaking in a tiny mechanical model. We're naming a measured intrinsic quantum property that behaves according to rules related to rotation. It is real because it produces real effects. It is not literal spinning because there is no little extended object turning in the classical way. The word is a bridge from familiar motion to unfamiliar structure. Like all bridges, it is useful if we cross it, Not if we build a house in the middle and refuse to move. As this idea settles, the universe becomes a little less like a machine made from tiny versions of everyday things, and a little more like a set of deep rules that only sometimes resemble the world we can see. The electron is not a bead. The photon is not a speck of dust. The atom is not a miniature solar system. These images can help for a while, then they must be revised. Spin is one of the first places where the revision becomes unavoidable. The name invites a picture, the experiments deny the literal picture, and the quantum theory offers something stranger but better. From there, the next natural question is how physicists ever found such a property in the first place. If no one could watch an electron spin, and if the spin was not a visible rotation, what evidence forced the idea into physics? The answer came not from seeing a tiny object turn, but from watching beams split, spectral lines separate, and atoms respond to magnetic fields in ways that classical ideas could not explain. The hidden twist of particles revealed itself indirectly, through patterns too precise to ignore and too strange to fit the old mechanical imagination. That hidden twist first showed itself not as a picture, not as a little wheel, and not as some tiny object caught turning under a microscope, but as a stubborn pattern in experiments. This is often how nature speaks when the thing we are looking for is too small, too strange, or too unlike the objects our eyes were built to understand. We do not see the property directly. We see what it does. We notice where a beam lands, how a line of coloured light splits, why a magnet tugs one atom this way and another atom that way. Slowly a shape appears in the evidence, and the mind begins to say, there is something here that the old picture has missed. In the early days of atomic physics, scientists were surrounded by mysteries that were almost polite in how consistently they refused to go away. Atoms gave off light only in certain colours. Elements had spectral fingerprints, precise patterns of bright lines that appeared when their atoms were excited. These lines were not smooth rainbows. They were separated, ordered, and strangely particular. A little sodium, for example, could reveal itself by a pair of yellow lines, close together but not the same. Hydrogen had its own pattern. Mercury had another. Every element seemed to carry an internal musical scale, allowing some notes and forbidding others. This was already a clue that atoms were not tiny solar systems in the simple classical sense. If electrons were merely little planets circling a nucleus, they should have radiated energy continuously and spiraled inward. The atom should not have been stable. The light from atoms should not have appeared in narrow lines. Yet atoms were stable, and their light was sharply patterned. Something was being counted inside matter, something more exact than ordinary motion. Quantum theory began as an attempt to explain this counting. At first, the new theory described certain allowed energies. Electrons in atoms could occupy only particular states. They could jump between those states and give off or absorb light of specific colours. This was strange, but it worked. Then the details became even stranger. When scientists placed atoms in magnetic fields, some spectral lines split apart. The light that had once appeared as a single line became several close lines. This effect, named after Peter Zeeman, suggested that magnetism was reaching inside the atom and separating states that had looked identical before. The atom was not just a simple arrangement of energy levels, it had hidden distinctions. One way to understand this is to imagine listening to a choir from far away. At first, you hear one blended note. Then you move closer or the room grows quieter, and you realise the note is made of several voices. They were always there, but your earlier listening could not separate them. In the same way, magnetic fields reveal that atomic states had more internal structure than expected. The atom was not only choosing certain energy levels. Within those levels, there were finer differences, quiet internal labels that magnetism could expose. Scientists try to explain these splittings using the motion of electrons around the nucleus. If an electron moved in an orbit, perhaps that orbit created a kind of tiny current, and a current could behave magnetically. That idea captured part of the story. Moving charge does create magnetism. Orbital motion, in its quantum form, does matter, but it was not enough. Some splittings refused to fit. Some patterns needed an additional ingredient. The atoms seemed to be carrying a magnetic character beyond what orbital motion alone could provide. Then came one of the most elegant and unsettling experiments in the history of quantum physics, the Stern-Gerlach experiment. It was performed in the early 20th century by Otto Stern and Walter Gerlach. The setup sounds almost simple, though its meaning was anything but. They heated silver so that individual silver atoms formed a beam. This beam travelled through a region with a specially shaped magnetic field, a field that was stronger in one place than another. If the atoms carried tiny magnetic properties, the field would tug on them as they passed through. Afterward, the atoms landed on a screen, leaving marks that showed how they had been deflected. The classical expectation was fairly gentle. If the tiny magnetic orientation of each silver atom could point in any direction, the atoms should have been deflected by many different amounts. Some would be pulled strongly upward, some weakly upward, some not much at all, some weakly downward, some strongly downward, and everything in between. The screen should have shown a smeared band, a soft spread of impacts, because classical objects can have continuous orientations. A little magnet can point at any angle. A spinning object can tilt in endless ways. That is what everyday physics would suggest. But the silver atoms did not make a continuous smear. They split into two distinct beams. Two marks appeared, not one broad blur, not a smooth distribution, but two separated outcomes. It was as if the atoms, when asked by the magnetic field how they were oriented, could answer in only two ways. At the time, this was shocking. It revealed something deeply quantum about angular properties. The atom was not behaving like a tiny classical magnet pointing randomly through all possible angles. Its response was quantized. The word quantize simply means that the possible results came in separate allowed values rather than a smooth range. The silver atoms were making a choice from a very limited menu. Nature had replaced a dial with a switch. The full interpretation of the Stern-Gerlach experiment became clearer later, after the idea of electron spin entered physics. A silver atom has many electrons, but almost all of their angular and magnetic effect pair off and cancel. One outer electron remains as the main contributor to the atom magnetic behaviour. The splitting into two beams reveal the two possible outcomes associated with that electron intrinsic spin when measured along the chosen direction. The experiment did not show a tiny electron rotating. It showed that the electron carried a built-in quantum property that responded to a magnetic field in two distinct ways. There is something wonderfully quiet about the image. A beam of silver atoms passes through a magnet. The atoms are too small to see. Their inner properties cannot be watched directly. Yet on a detector, two traces appear, and those traces tell us that the old picture is incomplete. No fireworks, no dramatic cosmic collision, just a split beam in a laboratory, asking physics to change its mind. Before spin had a name, another mystery was already pressing on the theory. Wolfgang Pauli, one of the sharpest physicists of the 20th century, had introduced what he called a two-valuedness in the quantum description of electrons. He did not at first picture it as a literal spinning motion. He was cautious, precise, and allergic to careless imagery. But the patterns in atomic spectra demanded an extra quantum label, something that came in two possibilities and helped explain the fine structure of atoms. Pauli knew the electron needed another property. He could describe its necessity before anyone had a comfortable picture of what it meant. Then, in the mid-1920s, two young physicists, George Uhlenbeck and Samuel Gaudsmit, proposed that the electron itself possessed an intrinsic angular momentum. They called it spin. The idea was bold and in its first form still carried the flavour of a tiny rotating charged sphere. That picture had problems, as we have already seen. It strained against relativity and against the point-like nature of the electron. But the proposal captured something essential. The electron had its own magnetic character. It had an internal angular property independent of its motion around the nucleus. It could help explain atomic spectra and the two-valuedness Pauli had identified. There is a story often told about their hesitation. Uhlenbeck and Goudsmit were young, and when difficulties with the idea became apparent, they worried they had made a mistake. They reportedly wanted to withdraw their paper, but it had already been sent. In science, even a partly flawed picture can sometimes contain a true seed. The literal image of a spinning electron would not survive, but the idea of intrinsic spin would become central to quantum mechanics. This is a good moment to notice how discovery often works. It is not usually a clean staircase where every step is polished before the next one is taken. It is more like walking through fog with several lanterns. One lantern is experiment, another is mathematics, another is intuition, another is analogy. Sometimes one lantern shines clearly while the others flicker. The Stern-Gerlach experiment showed a split. Atomic spectra showed hidden structure. Pauli supplied a needed quantum label. Uhlenbeck and Goudsmit proposed intrinsic spin. Later theory would refine the idea, removing the naive mechanical picture and placing spin into a deeper framework. That deeper framework arrived with the development of quantum mechanics itself. The old quantum theory of orbits and jumps gave way to wave mechanics and matrix mechanics, two forms of a new theory that were eventually understood as different languages for the same physical structure. In this new theory, particles were described by states, and those states could contain components that had no simple classical counterpart. Spin became one of these components. It was not an extra little motion added onto an electron. It was part of the state space needed to describe the electron correctly. When Paul Dirac later built a theory of the electron that respected both quantum mechanics and special relativity, spin emerged naturally. This was one of the great triumphs of theoretical physics. Instead of being patched on by hand, the electron spin appeared as part of the proper relativistic quantum description. The theory also predicted antimatter, another sign that the mathematics was seeing farther than ordinary intuition. Spin was no longer merely an awkward guess inspired by spectral puzzles. It belonged to the deep structure of the theory. But it is useful not to race too far ahead. For the listener drifting through this story, the important thread is that spin was discovered through behaviour. It was not found by looking at a particle and seeing it rotate. It was inferred because atoms and particles responded to magnetic fields in ways that demanded an intrinsic quantum property. The evidence came from light, from magnets, from beams, from patterns that split where classical physics expected smears or different arrangements. The Stern-Gerlach experiment remains especially powerful because it makes the strangeness almost visible. Imagine a stream of atoms as a fine mist moving through a dark room. You cannot see each atom, but you know where they land. The magnetic field is not merely bending the stream as a whole, it is sorting the atoms into separate possibilities. In the classical picture, the mist should spread smoothly. In the quantum picture, it divides. That division is a signature of measurement in a world where some properties do not vary continuously. The silver atoms did not politely reveal all possible orientations. They gave two outcomes. And if the apparatus was turned, the meaning of those outcomes changed with the new direction of measurement. This is subtle. It is not that each atom carried a tiny arrow with a definite direction that the apparatus merely discovered in the ordinary sense. Quantum spin states do not behave like hidden arrows waiting in a pocket. The act of measuring spin along a particular direction gives a result tied to that direction, and the rules for different directions are not the same as the rules for ordinary three-dimensional arrows. This is one reason spin later became so important in discussions about the foundations of quantum mechanics. It reveals the difference between classical hidden properties and quantum states with unusual clarity. Still, in a calm introduction, we do not need to settle every philosophical debate. It is enough to feel the pressure that the experiments placed on old ideas. Classical physics expected continuity. Quantum experiments gave discreteness. Classical spinning required extended objects. Electron spin did not. Classical magnets could point in any direction. Quantum spin measurements returned specific allowed outcomes. Bit by bit, the familiar image gave way to a new one. One of the most important consequences appeared in the structure of atoms. Electrons occupy quantum states, and spin gives each electron an additional way to be distinguished within those states. Pauli exclusion, which we will soon wander into more deeply, says that certain particles, including electrons, cannot share the exact same quantum state. Spin helps determine what counts as the same state. Because electrons have two possible spin outcomes in a given orbital context, atomic shells fill in the patterns that create the periodic table. That means spin is not only a laboratory curiosity, it is part of the reason oxygen behaves like oxygen, carbon like carbon, iron like iron. It helps make chemistry possible in its familiar form. It is remarkable to think that a split beam of silver atoms points toward the architecture of matter. The experiment seems modest in its physical scale, but its implications reach into everything solid, liquid, and living. A quiet laboratory mark becomes connected to the way atoms hold electrons, the way elements differ, the way materials respond to magnets, and the way stars and planets contain the matter they do. This is often the beauty of physics. A small observation, if it is precise enough, can open a door into a vast structure. The discovery of spin also shows how misleading it can be to demand that nature make herself easy to visualize. The old picture of an electron as a tiny orbiting bead was already under strain. Spin made the strain worse if people tried to make it literal. But once physicists accepted that particles were described by quantum states rather than miniature mechanical parts, spin found its proper place. It became less like a hidden gear and more like a rule of identity. An electron is the kind of thing that has this spin. A photon is the kind of thing that has another. Other particles have their own spin types. These categories help organize the particle world. Spin became a way of classifying particles. Some particles have electron-like spin and obey one kind of collective behavior. Others have a different kind of spin and obey another. This difference is not just bookkeeping. It determines whether particles can crowd into the same state or prefer to share states freely. It affects matter, radiation, forces, and the stability of large systems. The hidden twist is not a decorative swirl. It is a sign of what family a particle belongs to and how it participates in the quantum world. The word hidden, though, should be handled gently. Spin is not hidden because physicists lack cleverness. It is hidden because it is not a visible motion. It reveals itself through the right interactions. A magnet can ask a spin question. A spectral line can display a spin consequence. A material can show collective spin behavior. A medical scanner can use nuclear spin to form images of the body. The property is hidden only from ordinary sight, not from physics. Once the right experimental language is used, spin speaks very clearly. And yet the history remains humbling. It took time for physicists to understand what the evidence was saying. First there were spectral lines, then line splittings, then unexplained two-valued properties, then beams dividing in magnetic fields, then a daring spin hypothesis, then a more complete theory that showed why spin belonged in the quantum description from the start. Each stage corrected the previous one without making it useless. The naive spinning picture was wrong in the literal sense, but it helped point toward a real, angular property. The early quantum labels were incomplete, but they guided the theory toward something deeper. Discovery was not a single flash. It was a sequence of adjustments. For a listener resting at the edge of sleep, perhaps the simplest picture to keep is this. Scientists noticed that atoms and electrons behaved as if they carried a tiny magnetic character that could not be explained by ordinary motion alone. When tested in magnetic fields, the outcomes came in distinct sets, not a continuous spread. To explain this, physics introduced an intrinsic quantum property called spin. Later, the deeper theory showed that this property was not a mechanical rotation, but a fundamental part of how particles exist and transform. This is why the title question has such a satisfying twist. If particles do not spin, why do they have spin? Because spin was never truly meant to be a tiny turning motion. It was the name given to a real quantum property discovered through its rotational and magnetic effects. The word came from a comparison, but the property outgrew the comparison. Like many scientific names, it carries a fossil of an earlier image inside it. There is something almost human about that. We name what we only partly understand. We reach for familiar language. We say the electron spins because something about it acts like angular momentum, because something about it behaves magnetically, because the mathematics of rotation seems to recognize it. Then, as the idea matures, we learn to hear the word differently. Spin becomes not a picture of motion, but a clue to structure. From this point, the path leads naturally into the way physicists label quantum properties. Spin is one label among others, but it is a particularly important one because it helps organize particles, atoms, and matter itself. The small world is full of such labels, not labels in the casual sense, but measured features that define what states are possible and how systems behave. Once we understand why spin had to be introduced, we can begin to see it as part of a larger catalogue of quantum identity, a catalogue where nature keeps track of energy, charge, angular behaviour, and the allowed arrangements of matter with a precision no ordinary filing cabinet could ever hope to match. The small catalogue of quantum identity begins with a simple realisation. An atom is not described well by saying only that it contains a nucleus and some electrons. That is true, but it is too rough, a little like describing a whole library by saying it contains books and shelves. The statement is not wrong, but it misses the order that makes the library useful. Books are arranged by subject, author, title, date, and location. Without those labels, the library becomes a room full of paper. In a similar way, an atom is not just a nucleus with electrons somewhere nearby. It is a carefully organised quantum system, and the electrons in it are described by a set of labels that tell us what kind of state each electron occupies. These labels are called quantum numbers. The name sounds a little dry, as if it belongs on a dusty chart pinned to a classroom wall, but the idea is quietly beautiful. Quantum numbers are the ways nature keeps track of what is allowed inside an atom. They are not serial numbers stamped onto tiny beads. They are not luggage tags tied to particles as they move around. They are measured features of quantum states, the allowed patterns that electrons can have around a nucleus. They help tell us the energy of an electron, the general shape of its allowed region, the angular character of that region, and the spin state that comes along with the electron itself. If the word state feels a little slippery, it helps to slow down. In everyday life, an object has a position and a motion. A thrown ball is here, moving that way with a certain speed. A planet is there, orbiting the sun. A pen rests on a desk. Classical objects seem to have definite properties all the time, whether or not anyone checks. Quantum objects are described differently. An electron in an atom is not a tiny bead following a neat little path around the nucleus. It is described by a quantum state, a pattern of possibilities with definite allowed properties. Those allowed properties are what the quantum numbers name. The old picture of electrons orbiting like planets was useful for a while, but it had to be replaced. If electrons were simply little planets, atoms would not behave the way they do. They would radiate energy, collapse inward, and fail to produce the sharp patterns of light that experiments reveal. Instead, electrons occupy standing wave-like patterns around the nucleus. That phrase should not be taken too literally either, but it is closer than the planet picture. Think of a vibration on a string, where only certain patterns fit. The string can hum in one allowed pattern, then another, but not every possible pattern in between. Atoms are not strings, of course, but the comparison helps. Electrons in atoms occupy allowed patterns, and quantum numbers are the labels for those patterns. One label is connected to energy and size. It tells us, roughly speaking, how far out from the nucleus the electron state tends to extend and how much energy is associated with it. Electrons closer to the nucleus are usually more tightly bound, while those in larger states are held less tightly. This is not like planets orbiting at fixed tracks, but there is still a sense of inner and outer regions. The first label gives the broad shell, the main address, the general floor of the atomic hotel. It says whether the electron belongs to a compact low-energy state or to a larger, more extended one. The word shell comes from the old visual language of atoms, and although the real quantum picture is softer, the word remains useful. Another label describes the shape or angular style of the state. Some electron states are spherically balanced around the nucleus. Others have more directional structure, with lobes and patterns that become important in chemistry. These shapes are not hard containers. They are maps of probability, ways of describing where an electron is likely to be found if measured. A common mistake is to imagine an orbital as a little room where the electron runs around inside. It is better to think of it as the shape of the electron state itself, a pattern spread through space. Some patterns are simple and round, others are more complex, reaching in certain directions like quiet, invisible petals. These shapes help determine how atoms bond, how molecules form, and why matter has such variety. A further label describes orientation. If an electron state has a directional shape, it can be arranged relative to space in different allowed ways. In a magnetic field, these different orientations may no longer have the same energy. They can split apart, which is one of the reasons spectral lines separate in experiments. Again, nature does not offer every possible classical angle in the same way a little object might. The allowed values are discrete. The atom behaves as if only certain orientations count. This is one of the recurring signatures of quantum mechanics. The small world often replaces smooth choice with permitted steps. Then there is spin. Spin is another quantum label, but it is not merely another detail of the orbital pattern. It belongs to the electron itself. Every electron carries the same intrinsic spin, and when measured along a chosen direction, that spin gives one of two possible outcomes. The electron may occupy the same kind of orbital region as another electron only if the total quantum state is not identical, and spin provides part of the distinction. This is why spin becomes essential when atoms fill with many electrons. It helps decide who can sit where in the quiet theatre of the atom. At first, these labels may sound like bookkeeping, but bookkeeping can be powerful when the universe is strict about its records. Quantum numbers do not simply describe what scientists happen to notice. They determine which states exist, which transitions can occur, and which arrangements are forbidden. They explain why electrons do not all collapse into the lowest available condition. They help build the periodic table. They reveal why elements have repeating chemical patterns. They are small labels with large consequences. Imagine trying to seat guests at a formal dinner where nature has unusual rules. Some seats are grouped by table. Some tables have different shapes. Some seats face different directions. Each guest has an additional two-way personal marker that affects whether they may share a table position with someone else. You cannot simply put everyone wherever you like. The seating plan has rules, and the entire character of the evening depends on them. In an atom, quantum numbers are part of that seating plan. They tell electrons which states are available and how those states may be filled. The most famous rule connected to this atomic seating plan is the Pauli exclusion principle. We will give it more space soon because it deserves it, but a gentle preview helps here. The rule says that no two electrons in the same atom can have the exact same complete set of quantum numbers. In plainer words, two electrons cannot be identical in every part of their quantum address. If they share the same broad shell, the same shape label, and the same orientation label, then their spin labels must differ. This is why an orbital can hold a pair of electrons with opposite spin outcomes along a chosen direction. They are similar in many respects, but not completely identical. That small difference matters enormously. Without spin, or without the exclusion rule tied to particles like electrons, atoms would not fill in the way they do. The structure of the periodic table would fall apart. Chemistry would not have its familiar architecture. The difference between carbon and nitrogen, oxygen and fluorine, sodium and magnesium, depends on how electrons occupy quantum states. Those occupations depend on quantum numbers. The identity of an element is determined by the number of protons in its nucleus, but its chemical behavior depends greatly on how its electrons arrange themselves. Quantum labels shape that arrangement. This is one of the places where a technical idea becomes suddenly intimate. The hardness of a mineral, the smell of rain on stone, the way salt dissolves in water, the way oxygen supports breathing, the way carbon forms the backbone of living molecules, all of this depends on electron states and the rules for filling them. Quantum numbers are not distant abstractions hidden in a laboratory. They are part of why the world has textures, reactions, colours and forms. They are tucked beneath ordinary experience. A flame, for instance, has colour because atoms and molecules exchange energy in specific ways. Electrons move between allowed states, and the light released carries the difference between those states. If electron states were not labelled and limited by quantum rules, atomic light would not have the same sharp signatures. Spectroscopy, the science of reading light from matter, depends on the fact that atoms have structured internal states. When astronomers identify elements in a distant star, they are using patterns that come from quantum numbers. The tiny labels inside atoms become messages crossing space. This is a lovely reversal of scale. Quantum numbers describe states inside atoms far too small to see. Yet because those states shape light, they allow us to learn what stars are made of across enormous distances. A label inside an atom becomes a line in a spectrum. A line in a spectrum becomes knowledge about a star. A star becomes part of a larger story about galaxies, chemistry, planets, and life. The tiniest bookkeeping reaches the widest sky. Spin has a special role in this catalogue because it is not just a label for where an electron is likely to be around a nucleus. It is tied to the identity of the electron as a particle. The electron does not gain spin because it enters an atom. It already has spin. The atom gives the electron possible states to occupy, and spin becomes part of the complete description of those states. This is why spin is both internal and relational. It belongs to the electron, but it matters in how the electron fits into larger systems. When two electrons occupy the same orbital region in an atom, their spins must pair in a way that keeps their complete descriptions distinct. This pairing is one of the quiet habits of matter. Electrons often settle into pairs, and when all spins are paired, the atom or molecule may have little net magnetic character. But if spins remain unpaired, the material can behave differently in a magnetic field. This is one reason transition metals and certain compounds have rich magnetic behavior. The details can become complex, but the basic idea is calm enough. Spin labels help determine whether magnetic tendencies cancel or remain. This helps explain why spin appears again and again in different parts of physics. It is not confined to one corner of atomic theory. In atoms, it helps organize electrons. In solids, it helps produce magnetism. In nuclei, it plays a role in magnetic resonance. In particle physics, it helps classify particles. In quantum information, it can serve as a delicate carrier of quantum states. The same basic property, first introduced to explain puzzling measurements, becomes a thread running through many technologies and theories. But to appreciate quantum numbers fully, it is important to resist picturing them as hidden digits printed on particles. An electron does not carry a tiny tag that says its shell and shape and orientation in ink. These are labels we use for states, not little physical stickers. The labels describe how the state behaves, what measurements can reveal, and how the state fits into the allowed structure of the system. They are more like musical notes than inventory numbers. A note in a song is not a physical object separate from the vibration. It is a way of describing the vibration itself. Similarly, a quantum number describes a feature of the quantum state. The music comparison is useful because atoms really do have something like allowed harmonies. Not all patterns fit, only certain standing arrangements are possible. The electron states around a nucleus resemble the allowed modes of a system, though in a deeply quantum way. Each mode has labels. The labels help determine how electrons can fill the modes, how they can move between them, and what light may be absorbed or emitted. Matter is not a random crowd of particles. It is more like a vast arrangement of permitted notes, and spin is one of the properties that decides how those notes may be combined. Still, there is no need to make the picture too delicate or poetic. The practical meaning is direct. Quantum numbers tell physicists what state an electron is in. They allow predictions, they explain experiments, they organize the periodic table, they help describe atoms, molecules, and materials. They are necessary because the old classical description does not have enough information. In classical physics, one might try to describe an electron by position and velocity. In quantum physics, an electron in an atom is described by a state with allowed labels. Those labels do the work that the old orbit picture could not. One of the reasons this can feel strange is that everyday objects do not seem to need quantum numbers. A cup on a table does not appear to have a set of tiny labels defining its allowed states. It simply sits there. But the cup is made of atoms, and those atoms are built from quantum states. At large scales, the countless quantum details blend into familiar classical behavior. The cup has a position, a temperature, a shape, and a weight. But beneath that ordinary description is an enormous number of microscopic arrangements, each governed by quantum rules. The calm surface of the world hides a crowded precision underneath. This is also why quantum numbers are not optional decorations in a textbook. If we remove them, atoms lose their explanation. Why do electrons form shells? Why do elements repeat their chemical properties in rows? Why do noble gases resist bonding? Why do some atoms form one bond while others form 2 or 4? Why do spectral lines split in magnetic fields? Why does matter occupy space instead of collapsing into a featureless dense state? Again and again, the answers point back toward allowed quantum states and the labels that describe them. Spin enters the story as the label that looks most misleading because of its name. The other labels may sound technical, but spin sounds familiar. That familiarity makes it easy to imagine the wrong thing. Yet in the atomic catalogue, spin is simply one of the essential entries in the full state description. It tells us how the electron intrinsic angular property is arranged relative to a measurement direction. It gives 2 possible outcomes for an electron when measured along that direction. It helps distinguish one electron state from another. That is enough to reshape the architecture of matter. There is a pleasant humility in this. Nature does not require large dramatic causes to produce large dramatic results. A 2-way quantum label, repeated across electrons in atoms, contributes to the differences between elements. Those differences build chemistry. Chemistry builds the complexity of the world. What seems like a tiny distinction becomes part of everything from the air to the oceans to the proteins in a cell. Spin is small only in scale, not in consequence. The universe is full of such tiny labels. Electric charge tells particles how they respond to electromagnetic fields. Mass tells us about inertia and gravitational behavior. Spin tells us about intrinsic angular character and how particles transform under rotations. Other properties appear in particle physics, where particles are classified according to additional internal features. Some of these labels feel less familiar than spin, but they serve a similar purpose. They organize what particles are and what they can do. Physics, in this sense, is not just a study of objects, but a study of permitted identities and relationships. For electrons in atoms, the complete set of quantum labels acts like an address. Not an address in ordinary space, because an electron orbital is not a little apartment with walls, but an address in the space of possible states. It tells us the shell, the pattern, the orientation, and the spin condition. If 2 electrons try to share every part of that address, the exclusion rule says no. If their spin labels differ, they may occupy the same orbital pattern as a pair. This simple idea turns out to be one of the central organizing principles of atomic structure. We can imagine the periodic table now as more than a chart of element names. It is a map of electron filling. Each row and column reflects how quantum states are occupied as nuclear charge increases. The table is not just a human filing system. It mirrors the quantum architecture of atoms. The reason elements in the same column often behave similarly is that their outer electrons have similar arrangements. Those arrangements depend on quantum numbers. The chemistry classroom chart is, underneath its coloured boxes, a quiet monument to quantum mechanics. And spin is written into that monument, not as a visible swirl, not as a tiny arrow carved into each box, but as part of the rule that allows two electrons into many orbital states, and then requires the next electrons to move on to other available states. If all electrons could simply pile into the lowest state, there would be no rich shell structure. Matter would be profoundly different. The world would not have the layered variety we know. Spin, together with exclusion, helps prevent that collapse into sameness. This is why learning about quantum numbers can change the feeling of the word particle. A particle is not just a speck. It is an entity with identity, responses, and allowed ways of being. An electron is not interchangeable with a grain of dust made tiny. It carries charge, mass, spin, and quantum behavior. When bound in an atom, it occupies states described by quantum labels. Those labels are not arbitrary names. They are how the electron participates in the ordered structure of matter. As the idea settles, the earlier mystery of spin becomes a little clearer. Particles have spin because spin is one of their quantum properties, one of the labels needed to describe how they behave. It is not there because something inside them is rotating like a wheel. It is there because the particle belongs to a certain kind of quantum representation of nature, a certain kind of behavior under rotations and measurements. In atoms, that property becomes part of the full address of electron states. It helps decide which arrangements are allowed and which are not. The next step is to see what happens when that tiny label is taken seriously across many electrons. The Pauli exclusion principle is where spin stops being only a mysterious property and becomes one of the reasons matter has structure at all. It is the rule that prevents electrons from all crowding into the same lowest condition, the rule that builds shells, supports chemistry, and quietly helps make solid objects solid. To follow it is to watch a small quantum distinction become the architecture of the visible world. Once the idea of quantum numbers is in place, the phrase spin up and spin down begins to sound almost too tidy. Up and down are comfortable words. They belong to staircases, shelves, falling rain, raised hands, sleepy eyelids, and the quiet decision to turn a pillow over to the cooler side. They make it seem as if the electron is carrying a tiny arrow, and that arrow is either pointing upward like a weather vane in a gentle breeze, or downward like a tired flower at the end of a hot day. It is a useful first image, but like so many images in quantum physics, it must be handled with care. Electrons do have spin states that we call up and down when we measure them along a chosen direction, but the electron is not simply a tiny object with a little painted arrow fixed inside it. Up and down are names for measurement outcomes. They are part of the language physicists use to describe how spin reveals itself. The reason these words appear at all has much to do with magnetism. An electron carries electric charge, and it also has spin. Together, these facts give the electron a small magnetic character. It behaves as if it has a tiny magnetic personality, something that can interact with an external magnetic field. This does not mean there is a miniature bar magnet glued inside the electron, with a north end and a south end made of tiny metal. It means that when the electron is placed in a magnetic field, its spin is connected to energy, direction, and measurable response. Magnetism gives spin a way to show itself. In ordinary life, magnets are among the most familiar magical objects that are not actually magical. A fridge magnet holds a note in place. A compass needle turns toward north. Two magnets can snap together or push apart without visible contact. We learn these effects as children before we know anything about fields, electrons, or quantum mechanics. A magnet feels like a small invitation to wonder because it makes empty space seem active. Something unseen reaches across the gap. At the deeper level, magnetism is not empty space doing nothing. It is the behavior of electromagnetic fields and charged particles. In many everyday magnets, the source of the large magnetic effect is connected to electrons inside the material. Electrons have spin, and that spin carries magnetic behavior. In most materials, the magnetic effects of electrons are paired or arranged so that they cancel out. The material as a whole does not act like a strong magnet, but in certain materials, many electron magnetic contributions can line up in a coordinated way. Then the hidden spin behavior of countless electrons becomes visible at the scale of a hand, a kitchen door, or a compass. This is one of the loveliest bridges between the quantum world and the everyday world. A property that is not a literal spinning motion, a property that cannot be seen directly, can still gather together across trillions of particles and produce something as ordinary as a magnet sticking to metal. The fridge magnet is not a simple thing. It is a quiet chorus of quantum order. To understand the mystery of up and down, imagine an electron entering a region where a magnetic field points in a chosen direction. Physicists may call that chosen direction up, but this is a convention. It is not that the universe has a permanent ceiling and floor. The measuring device defines the direction being tested. If the apparatus is turned sideways, then sideways becomes the new reference. If the apparatus is tilted, the measurement question changes. Up and down in spin are not universal labels floating through the cosmos. They depend on how the measurement is arranged. This is already different from an ordinary arrow. If you hold an arrow in your hand, it has a direction in space. You can look at it from many angles, but the arrow is simply pointing where it is pointing. If it points north, it points north. If it points upward, it points upward. Quantum spin is subtler. When we measure an electron spin along a chosen direction, the result comes out as one of two possibilities. We call those possibilities up and down relative to that direction. But before measurement, the electron state may not be equivalent to a little arrow already pointing in one definite classical direction. The state can carry possibilities that do not fit the ordinary picture of hidden definite orientation. This is where the old intuition tries to sneak back in. It says, perhaps the electron really does have a tiny arrow, and we simply do not know which way it points until we look. That sounds reasonable, but quantum experiments have taught us that this classical hidden arrow picture cannot explain everything. The electron spin state behaves in ways that are not the same as an ordinary object with a pre-existing direction. Measurements along different directions do not merely reveal different components of a fixed little arrow. They follow quantum rules, and those rules include probabilities, state changes, and outcomes that depend on the measurement context. Still, it is helpful not to make the idea too mystical. The electron is not choosing out of confusion. The experiment is not vague. The results are exact in the way quantum mechanics predicts. If many electrons are prepared in the same spin state and measured along the same direction, physicists can predict the pattern of outcomes. The individual result may be one of two possibilities, but the overall behavior follows strict rules. Quantum physics is not a fog of anything goes. It is precise, even when it is not picturable in the old mechanical way. The words spin up and spin down came from the practical need to name these two outcomes. A magnetic field can separate particles according to their spin response. One group may be deflected one way, another group the opposite way. If the measuring direction is vertical in the laboratory, it feels natural to call the outcomes up and down. But the words should not hypnotize us. They do not mean the electron contains a tiny arrow that must always be either vertical up or vertical down. They mean that along the chosen measurement direction, the spin measurement has two possible answers. A compass needle gives a useful contrast. A compass is a classical magnetic object. It can rotate smoothly. It can point northeast, southwest, or any direction between. If you place it in a magnetic field, it tends to align continuously. Its needle may wobble and settle. You can watch the motion. Its direction is visible. Electron spin does not behave like a little compass needle that can be seen turning through all angles. When measured along a direction, it gives discrete outcomes. This is the quantum difference. Nature does not hand us a tiny needle. It hands us a rule for possible results. The old Stern-Gerlach experiment remains the clean doorway into this idea. Atoms passed through an uneven magnetic field and landed in separate places. Classical expectation suggested a smear, because tiny magnets with random orientations should have produced many possible deflections. Instead, the beam split into distinct parts. That split told physicists that angular magnetic behavior in the small world was quantized. The system did not reveal every possible tilt, it gave allowed outcomes. For electrons, the two-outcome structure is central. If we measure spin along one direction, we get one of two results. If we then immediately measure along the same direction again, we get the same result. In that sense, the first measurement prepares the electron in a definite state relative to that direction. But if we measure along a different direction afterward, the certainty can disappear. The electron may now give either result relative to the new direction, with probabilities determined by the relationship between the two measurement directions. This is not how a hidden little arrow would behave in ordinary classical physics. It is one of the simple but deep ways quantum spin reveals its unusual nature. A gentle way to picture this without making it false is to think of the measurement as asking a yes or no question. Not any question, but a very specific question defined by the apparatus. Are you spin up along this direction? The electron answers with one of two possible outcomes. If you ask the same question again right away, you get the same answer. But if you rotate the question and ask about a different direction, you're no longer asking the same thing. The state that gave a definite answer before may now give uncertain answers. The electron was not carrying a complete sheet of pre-written answers for every possible direction in the ordinary sense. It was carrying a quantum state, and the act of measurement draws out an answer according to quantum rules. This is why spin is so often used in introductions to quantum measurement. It is simple enough to name, yet strange enough to reveal the core difficulty. A particle with spin gives discrete outcomes. The outcome depends on the direction measured. The measurement can change the state. Repeated measurements along the same direction behave predictably, while measurements along changed directions expose probability. In a small and manageable way, spin contains much of the quantum mystery. Magnetism is the practical handle on that mystery. Because the electron spin is associated with a magnetic effect, magnetic fields can be used to manipulate spin states. A magnetic field can make one spin orientation have a different energy from another. It can cause spin states to evolve. It can allow physicists to prepare, control, and read out spin behavior. This is not merely theoretical. Technologies use these facts. Magnetic resonance imaging, for example, depends on the spin of atomic nuclei, especially hydrogen nuclei in the body. The machine uses strong magnetic fields and radio waves to influence and detect nuclear spin behavior. The result is a medical image, a detailed view of tissues inside a living body, made possible by a quantum property that is not literal spinning. This is a remarkable thing to pause on. A person lies in a scanner. The machine hums. Inside the body, nuclei respond to magnetic fields because they have spin. That response is measured and translated into images. A property discovered through atomic puzzles becomes part of modern medicine. Quantum spin leaves the blackboard and enters the hospital. Electrons also matter in technology through magnetism in solids. In magnetic materials, the arrangement of electron spins can create large-scale magnetic order. In some materials, neighbouring spins tend to align. In others, they prefer alternating patterns. In still others, the behaviour is disordered or delicate. These arrangements shape whether a material becomes a permanent magnet, how it responds to external fields, and how it can be used in devices. Spin is part of the hidden life of materials. The phrase up and down becomes more complex in a material because there are many electrons, many local environments, and many interactions. Yet the basic language remains useful. Spins can align with or against a chosen direction. They can pair and cancel. They can form domains, regions where many magnetic contributions line up. A piece of iron can contain many domains, and when enough of them align, the material acts as a magnet. The everyday magnet is not one giant simple spin, but a collective arrangement of many microscopic magnetic contributions. There is another subtle point here. The electromagnetic behavior is connected to spin, but the direction of the magnetic effect and the direction of spin have a relationship shaped by the electron charge. Because the electron is negatively charged, some of the intuitive arrow language can become backward if pushed too literally. For a calm explanation, the safest path is not to chase arrow pictures too far. The main point is that spin and magnetism are linked, and magnetic fields can distinguish between spin states. The details are precise, but the everyday arrow image can become misleading quickly. This is one reason physicists are comfortable using abstract language. They might speak of a spin state being aligned or anti-aligned with a magnetic field, but they know this is shorthand within a theory. The real content is in the measurable energy differences, deflections, transition frequencies, and probabilities. The language is useful, but it is not a tiny cartoon of the electron. The mystery of up and down also teaches us that direction in quantum mechanics is not always the same as direction in ordinary geometry. A classical object can have a direction because its parts occupy space in a certain arrangement. A quantum spin state has directional behavior because of how it transforms and how it responds to measurement. The difference is subtle but important. Spin has an angular character without requiring an object extended in space. It is directional in a quantum sense, not in the sense of a little stick pointing through the electron. If this feels slippery, it may help to remember that we accept invisible directional properties in other contexts. A magnetic field has a direction at each point, though we do not see it directly. We infer it by how compasses, charges, and currents respond. The wind has direction because leaves move, and skin feels pressure. We do not need to see a little arrow painted in the air. We understand direction through effects. Spin direction is even more abstract, but the principle of inference remains. We know it by what measurements show. Still, spin goes beyond ordinary hidden direction because of its quantum to-outcome nature. That is the part that makes up and down mysterious. If it were only an invisible arrow, the story would be simpler, but the electron does not behave as a classical arrow with all directions already settled. The measurement outcome along one direction does not give a complete classical description for all other directions. This is not a failure of knowledge, it is a feature of the quantum state. One of the profound lessons here is that measurement is not passive in the same way it seems in everyday life. If you look at a sleeping cat on a chair, you do not normally think your glance creates the cat position. The cat was there before you looked, probably judging the room in silence. In quantum mechanics, measuring certain properties can be part of bringing a specific outcome into being from a state of possibilities. With spin, measuring along a direction gives a definite result and prepares the state relative to that direction. The next measurement depends on that preparation. This does not mean consciousness is magically making reality. It means the physical interaction between system and measuring device is part of the quantum process. The calm, practical takeaway is that spin up and spin down are not permanent little labels independent of every measurement arrangement. They are outcomes relative to a chosen measurement direction. The same electron can be prepared as up along one direction, but that does not mean it is definitely up or down, along every other direction in the classical sense. This is why quantum spin is such a compact lesson in the difference between the old world picture and the new one. Magnets make this lesson tangible. A magnetic field can define the direction. The electron's spin state responds. The outcome can be recorded, the state can be prepared, the experiment can be repeated. Out of this comes a disciplined understanding, not of a tiny spinning ball, but of a quantum property with real magnetic consequences. Now let us turn back toward atoms. Electrons in atoms have both orbital states and spin. The orbital states describe the allowed patterns around the nucleus. Spin adds an intrinsic two-way label. In a magnetic field, the energy of an electron state can shift depending on how its magnetic behavior relates to the field. That shift can split spectral lines. This was one of the clues that spin was needed. Light from atoms carried the evidence. The colours did not merely glow, they testified. This is a lovely idea. The glow of an element in a flame or a discharge tube can contain information about electron states, magnetic interactions, and spin. A line in a spectrum is like a quiet signature. When lines split, the signature becomes more detailed. The atom is telling us that what seemed like one state was actually several possibilities separated by hidden labels. Spin is one of those labels, and magnetism is one of the ways it becomes visible. The up and down language also becomes important when the electrons pair. In many atoms and molecules, two electrons can occupy the same spatial orbital pattern, only if their spin states differ. We often describe this as one up and one down, again relative to a chosen convention. Their magnetic effects may cancel, leaving no unpaired spin. But if an electron is unpaired, its spin can contribute to magnetic behavior. This is why some atoms and ions are attracted to magnetic fields while others are not. The difference can come down to whether electron spins are paired or unpaired. At the scale of materials, many unpaired spins can interact. Sometimes they remain disordered, pointing in varied quantum arrangements so that no strong overall magnet appears. Sometimes they align cooperatively. When enough align, the material develops magnetization. The simple classroom image of many tiny arrows all pointing the same way is not completely useless here, but it must be remembered as a model, not the literal inside of each electron. The collective effect is real. The tiny arrows are a convenient sketch of spin alignment, not a photograph of microscopic reality. This is how physics often works across scales. At one level, we use a simplified picture that captures the useful pattern. At another level, we refine it. For a magnet, we may draw arrows to show domains. For an electron, we avoid imagining a tiny physical arrow. The same word can behave differently depending on the level of description. Good understanding is knowing when a picture helps and when it begins to lie. The mystery of up and down is therefore not just about electrons. It is about how we speak of nature when our ordinary images are too small for the truth. We use words like up and down because experiments have directions and outcomes. We use words like spin because the property has angular character. We use arrows because they are convenient. But behind the words is a quantum state, a set of rules for what can be measured and how the results appear. There is no need to feel disappointed by this. A less literal picture can still be a richer one. The electron is not reduced by losing its tiny cartoon arrow. It becomes more interesting. Its spin is not a miniature mechanical motion, but a fundamental property that helps organize atoms, create magnetic materials, enable medical imaging, and reveal the strange logic of quantum measurement. Up and down are not childish simplifications. They are useful names for deeply non-classical outcomes. As we keep moving, this spin label will become even more important. It does not merely explain how electrons respond to magnets. It helps explain why electrons refuse to crowd into the same state. That refusal, known through the Pauli exclusion principle, is one of the reasons matter has size and structure. The firmness of the world, the layering of atoms, the repeating order of the periodic table, and the chemical variety of matter all depend on the rule that electron states cannot be copied without limit. Spin supply is part of the identity that makes that rule work, and the humble words up and down become part of the reason the world does not collapse into sameness. That refusal to crowd together is one of the most important quiet rules in the universe. It is not loud, not visible, and not something we feel as a separate force in daily life. yet it helps explain why matter has structure, why atoms have layers, why chemistry has variety, and why the chair beneath you does not allow you to sink through it as though it were only a mist. The rule is called the Pauli exclusion principle, named after Wolfgang Pauli, and although the name sounds formal, the idea is direct enough to begin gently. Certain particles, including electrons, cannot occupy the exact same quantum state as one another. They may be close, they may belong to the same atom, they may share the same general orbital region if other parts of their description differ, but they cannot be identical in every quantum label at once. This rule is not a matter of politeness between particles. Electrons are not tiny guests choosing not to sit too close because they have good manners. They do not become embarrassed in a crowded atom. The exclusion principle is deeper than preference. It is built into the way electron-like particles exist. It is part of the structure of quantum mechanics. When we describe a system with more than one electron, the combined state must have a particular kind of behavior if two electrons are exchanged. That behavior leads to the exclusion rule. In simpler words, the mathematics of these particles does not allow two electrons to be complete copies in the same state. This is where spin becomes essential. Electrons belong to a family of particles called fermions. Fermions include electrons, protons, neutrons, quarks, and many other particles that make up matter. They have a kind of spin that leads to exclusion. Another family called bosons behaves differently. Bosons can share the same state freely in ways fermions cannot. Light particles are bosons, and so are certain particles that carry forces. That difference between fermions and bosons is one of the deep sorting rules of nature. Matter particles tend to resist being stacked into identical states. Force-carrying or field-like particles can gather together in shared states. The contrast helps shape the world. But for now, it is enough to focus on electrons. An electron in an atom has a state described by several quantum labels. There is the broad energy shell. There is the shape of the orbital state. There is the orientation of that state. And there is the spin label. The Pauli exclusion principle says that no two electrons in the same atom can have all of those labels identical. If two electrons share the same orbital state, their spin labels must differ. That is why many atomic orbitals can hold a pair of electrons, commonly described as one spin up and one spin down relative to a chosen direction. The words up and down remain shorthand, but they are useful shorthand. They show how spin gives electrons a way to be distinct even when the rest of their state is the same. This small distinction creates large order. Imagine an atom with a nucleus at the centre, pulling electrons through the electromagnetic force. If electrons were allowed to pile without limit into the lowest available state, they would all crowd inward. The atom would not have the layered structure we know. There would be little reason for electrons to fill higher and higher states in the careful sequence that produces chemical behaviour. But because electrons cannot all occupy the same state, only a limited number can fit into each available condition. Once the lowest states are filled according to the rules, additional electrons must occupy other states. They are forced outward into higher shells and different patterns. Atomic structure grows from exclusion. That is one of the great surprises of physics. The size and structure of atoms are not explained only by attraction between negative electrons and the positive nucleus. Attraction pulls electrons inward, but exclusion prevents them from all becoming identical occupants of the lower state. The atom is shaped by both pull and prohibition. The nucleus attracts. Quantum rules restrict. Together they produce shells, orbitals, and the pattern of the periodic table. The periodic table is often introduced as a chart of elements, but at a deeper level, it is a map of electron arrangement. Hydrogen has 1 electron, helium has 2, lithium begins a new outer shell, carbon has a different outer arrangement from oxygen, neon completes a shell and becomes chemically reluctant, sodium begins again with a single outer electron, which is why it shares certain chemical tendencies with lithium. The repeating patterns of the table come from how electrons fill quantum states, and that filling depends on exclusion. Without the exclusion principle, the table would not have the same rows and columns. The personalities of elements would not repeat in the familiar way. This is why Pauli exclusion is not a small technical rule buried in atomic theory. It is part of the reason chemistry exists as a structured subject. Carbon can form complex bonds because of its electron arrangement. Oxygen reacts as it does because of its outer electrons. Noble gases are stable because their outer shells are filled. Metals conduct because their electrons behave in collective ways shaped by available states. Every chemical reaction, every molecule, every mineral, every protein, every drop of water depends on the permitted arrangements of electrons. Those arrangements are built under the supervision of the exclusion principle. It is tempting to imagine the principle as a kind of force pushing electrons apart, but that is not quite right. Electrons repel one another electrically because they have the same charge, and that repulsion is a real electromagnetic force. The Pauli exclusion principle is different. It is not a push in the ordinary sense. It is a restriction on possible quantum states. Still, its effects can feel force-like when many particles are involved. If you try to compress matter, you're trying to squeeze electrons into a smaller set of available states. Because electrons cannot all occupy the same state. Compressing them forces some into higher energy states. This creates a resistance to compression. That resistance is sometimes called degeneracy pressure. The word pressure may sound more familiar. A gas pushes on the walls of a container because its particles move and collide. Degeneracy pressure is not exactly that kind of pressure. It arises from quantum exclusion. Even at very low temperatures, when ordinary thermal motion is reduced, fermions can still resist being squeezed into identical states. This effect becomes especially important in extreme objects such as white dwarf stars. A white dwarf is the dense remnant of a star that has exhausted its nuclear fuel. Gravity tries to crush it inward, but electron degeneracy pressure resists the collapse. The star can remain supported not by heat in the usual way, but by the quantum refusal of electrons to share the same states. In even denser objects such as neutron stars, a related kind of pressure involving neutrons becomes important. Neutrons are also fermions, and they too obey exclusion. A neutron star is unimaginably dense by everyday standards, packing more mass than the Sun into a city-sized region. Its existence is a dramatic astrophysical consequence of the same family of quantum rules that help structure atoms. The principle that keeps electrons from crowding inside an atom also helps matter resist collapse in some of the densest objects in the cosmos. A rule born in the small world reaches all the way to dead stars. Returning to ordinary matter, the exclusion principle also helps explain why solid objects feel solid. When your hand rests on a table, the atoms in your hand approach the atoms in the table. Their electron clouds interact. Electromagnetic repulsion matters, but so does the exclusion principle. Electrons in one object cannot simply enter already occupied states in another object without rearranging the combined system. As atoms are forced close together, their electron states resist being compressed into overlap. This contributes to the firmness and impenetrability we experience. The table is not solid because it is full of tiny hard marbles touching one another. It is solid because electromagnetic fields and quantum rules together make matter resist being pushed through itself. This is a subtle but important correction to the everyday image of solidity. Atoms are mostly space if we picture them with a tiny nucleus and a much larger region of electron probability. But that does not mean matter is empty in the sense that objects should pass through each other. The electron states around atoms create real interactions. The fields are real. The exclusion rules are real. When two pieces of matter meet, their quantum and electromagnetic structures do not simply ignore each other. They respond, resist, and rearrange. The result is the ordinary firmness of things. So when someone says matter takes up space, the deeper answer is not that every particle is a tiny hard ball with a fixed surface. It is that matter is made of quantum fields and particles whose states cannot all be made identical, whose charges interact and whose electrons occupy structured regions. The apparent volume of matter comes from the behavior of these states. The chair holds you up because of forces and rules operating between atoms, not because the atoms are like little stones packed tightly without gaps. The true story is less like a pile of gravel, and more like an invisible architecture of allowed and forbidden arrangements. Pauli himself was a famously sharp and sometimes severe figure in physics. He had a reputation for cutting criticism, and physicists joked about the Pauli effect, the supposed tendency for equipment to fail when he entered a room. Whether or not the joke was fair, his principle was one of the great clarifying ideas of quantum theory. It explained patterns in atomic spectra and electron configurations that had been puzzling scientists. Pauli first introduced the need for an extra two-valued quantum property before spin was fully understood. Later, when electron spin was proposed, it fit naturally into the structure his principle required. Spin gave electrons the additional label that allowed pairs to occupy the same orbital while remaining distinct. That relationship between spin and exclusion is one of the places where the question of this whole subject becomes especially meaningful. Particles do not spin like tiny tops, yet they have spin because spin is part of their quantum identity. That identity determines whether they obey exclusion and how they may share states. The consequences are not philosophical only, they are practical and material. Spin helps decide how electrons fill atoms. Exclusion helps decide the shape of matter. The fact that spin is not literal rotation does not make it less physical. It helps build the world. Let us imagine building an atom one electron at a time. The first electron settles into the lowest available state. A second electron can share the same spatial orbital because its spin label can differ. After that, another electron cannot simply become an exact copy of the first two. It must occupy a different state. As more electrons are added, the lower states fill and the next states become necessary. Step by step, shells form. Outer electrons determine much of chemical behavior. The atom becomes not a random swarm, but an ordered system with a recognizable structure. The order comes from allowed states and exclusion. This is why helium is so stable. Its two electrons fill the first shell. There is no easy low-energy place for another electron to join in the same compact arrangement. Lithium, with one more electron, must place that electron in a new outer shell. That outer electron is less tightly held and more chemically active. From this simple beginning, the larger periodic pattern unfolds. Filled shells tend to produce stability. Partly filled shells produce bonding possibilities. Spin and exclusion are quietly present in every row. The same principle helps explain why electrons in atoms often pair up. When two electrons share an orbital region with opposite spin labels, their magnetic effects can cancel. This affects whether an atom or molecule is magnetic. If all electron spins are paired, the material may not have strong permanent magnetic behavior. If unpaired spins remain, the material can respond more strongly to magnetic fields. Magnetism, chemistry, and atomic structure are not separate islands. They are connected through the rules governing electron states. The exclusion principle also shapes metals. In a metal, many atoms share electrons in a collective structure. The electrons fill available energy states up to a certain level. Because they cannot all occupy the same state, their arrangement creates a sea of occupied and unoccupied possibilities. This affects how metals conduct electricity and heat. When an electric field is applied, electrons near available states can respond and move through the material. The details require careful solid-state physics, but the broad idea is that exclusion helps determine how electrons fill the states of a material, and that filling helps determine whether the material behaves as a conductor, an insulator, or something in between. In semiconductors, the filling of electron states becomes even more important. Modern electronics depend on controlling which states are occupied and which are available. Transistors, computer chips, solar cells, and many sensors rely on quantum rules inside materials. The exclusion principle is part of the background structure that makes these technologies possible. When you use a phone, a computer, or any digital device, you're using matter whose electron states are arranged and controlled according to quantum principles. Pauli exclusion is not visible on the screen, but it helps make the screen possible. It can be surprising that a rule about not sharing states does so much work. But the universe often builds complexity from restrictions. Music becomes structured because not every sound is used at once. Language becomes meaningful because words follow rules and cannot be arranged in every possible way without losing sense. Architecture stands because materials have limits, and shapes must obey constraints. In atoms, electrons have constraints too. They cannot all be identical in state. That restriction creates layers, variety, and form. There is also a deeper reason the exclusion principle applies to electrons and not to every particle in the same way. It is tied to spin in a way known as the spin statistics connection. Particles with half-integer spin, spoken verbally here rather than written as a formula, are fermions and obey exclusion. Particles with whole number spin are bosons and can gather into the same state. This connection is one of the profound results of quantum field theory, linking spin, relativity, and the collective behaviour of particles. It is not an arbitrary rule pasted onto nature. It emerges from the deep consistency of the theory. This distinction explains why light can form intense coherent beams, such as lasers. Photons are bosons, so many of them can occupy the same state. A laser depends on that kind of shared behaviour. Electrons cannot do the same thing. They fill states one by one according to exclusion. Matter and light differ not only because one has mass, and the other travels through space at light speed, but also because their quantum statistics differ. Spin helps sort them into different collective behaviours. For daily life, the fermion side of the story matters most directly, because ordinary matter is made from fermions. Electrons, protons, and neutrons cannot all collapse into identical states. Their exclusion behaviour contributes to the structure of atoms, nuclei, and dense matter. The world has shape because the building blocks of matter do not behave like unlimited copies that can all occupy the same condition. They create a layered, resistant, structured reality. This does not mean exclusion alone explains everything about matter. Electromagnetic attraction and repulsion are essential. The strong nuclear force holds atomic nuclei together. Gravity shapes planets and stars. Thermal motion, chemical bonding, and many other effects matter too. Physics is rarely a single cause story, but the Pauli exclusion principle is one of the indispensable rules. Remove it, and the world as we know it would not survive. Atoms would lose their shell structure. Chemistry would be radically different. Solids, liquids, and the stability of matter would be transformed. The rule also helps explain why two objects do not simply merge when they touch. At the microscopic level, the electrons in one object cannot be freely placed into already occupied states in another. Their wave-like states must adjust to remain allowed. This adjustment costs energy, creating resistance. Along with electromagnetic repulsion, it gives rise to the contact forces we feel. When you press your hand against a wall, what you feel is not one set of tiny solid balls striking another set in the simple mechanical way. You feel the large-scale result of electromagnetic interactions and quantum restrictions between electron states. The wall pushes back because the quantum structure of matter does not permit effortless overlap. This can make ordinary touch seem more interesting. A fingertip on a table is not truly touching in the naive sense of tiny hard surfaces meeting. At the atomic level, electron clouds interact at a distance. The forces rise steeply as atoms are brought close. The exclusion principle contributes to that rise. The sensation of contact is your nervous system interpreting the resistance generated by fields and quantum rules. The world feels solid because of interactions, not because matter is solid in the old miniature billiard ball picture. Once again, the the deeper view does not make the world less real. It makes reality richer. The table is real, your hand is real, the pressure is real. But the explanation is not the obvious one our senses first suggest. Matter is not firm because it is made of tiny, impenetrable pellets. It is firm because quantum states and forces organize particles into structures that resist compression and overlap. Pauli exclusion is one of the quiet guardians of that organization. The word exclusion can sound negative, as if nature is merely forbidding something. But in physics, a prohibition can be creative. Because electrons are excluded from copying one another exactly, they are forced into diversity of states. That diversity produces shells. Shells produce chemical patterns. Chemical patterns produce molecules. Molecules produce materials, cells, atmospheres, oceans, and all the complicated arrangements that make the visible world. The no becomes a source of structure. There is a calm lesson in that. Not everything important happens because something pushes harder or moves faster. Some of the most important features of the universe arise from what is not allowed. The electron cannot be an exact duplicate of another electron in the same state. From that refusal, matter gains architecture. Atoms become layered. Stars resist collapse. Materials gain their properties. The ordinary world becomes possible. Spin remains tied to this entire story. If electrons did not have the spin they do, and if they did not belong to the Fermion family, exclusion would not shape atoms in the same way. Spin is not just a mysterious label that appears in magnetic experiments. It is linked to the collective behavior of matter. The fact that the electron has a certain kind of spin places it under the rules of fermions. Those rules govern how electrons fill states. The filling of states governs atomic structure. Atomic structure governs chemistry. Chemistry governs much of the world around us. This is why the question of spin cannot be separated from the question of matter. Particles do not spin in the everyday sense, yet their spin determines how they may exist together. It is not a tiny motion, but it has large consequences. It is not visible, but it changes what can be built. It is not a little rotation, but it helps decide the shape of atoms and the resistance of matter. It is one of the clearest examples of how quantum properties, even when hard to picture, are not distant from ordinary life. They are ordinary life at a deeper level. As the exclusion principle settles into the story, the next part of the puzzle becomes even stranger. Spin is connected not only to magnetism and matter, but also to the way quantum states respond when they are turned. Some particles behave in ways that have no familiar match in everyday rotation. An ordinary object returns to its starting appearance after one full turn. But the quantum description of an electron has a subtler behavior, one that requires a second full turn before it returns completely to itself. This does not mean the electron is physically spinning through two turns like a tiny dancer. It means the mathematics of its spin state belongs to a different kind of rotational structure. To understand why that matters, we need to move from shells and solids into the strange world of spinners, symmetry, and the surprising secret hidden inside a full rotation. The strange secret hidden inside a full rotation begins with something so ordinary that it hardly seems worth noticing. Turn a cup all the way around and it looks as it did before. Turn a book all the way around and the cover returns to its original direction. Turn yourself slowly in place, and after one complete turn, the room is back where it started. Everyday objects have a simple relationship with rotation. One full turn restores them. The handle of the cup comes back to the same side. The spine of the book faces the same way. Your nose points again toward the same wall. Nothing mysterious appears. The object may have moved, but once the turn is complete, its visible arrangement is restored. Quantum spin does not always follow this comfortable rule. Some quantum states, including the spin state of an electron, have a stranger relationship with rotation. The ordinary object comes back after one full turn. The electron spin state, in the deeper mathematical description, does not fully return in the same way until after a second full turn. In verbal terms, it takes a turn of 720 degrees for the spin state to come back completely. This is one of those facts that sounds like a trick when first heard. It can feel like someone is saying that a tiny object must turn twice to be the same. But that is not the right picture. The electron is not a little bead being spun through 2 full rotations. The statement is about how the quantum state associated with spin changes under rotation. To make sense of that, we need a word that may sound unfamiliar but is central to the story. The word is spinor. A spinor is a kind of mathematical object used to describe particles like electrons. It is related to rotation, but it does not behave like an ordinary arrow or a normal 3-dimensional object. This is why spinors are useful. If electron spin behaved like a little arrow, ordinary vector language would be enough, but it does not. The electron spin state responds to rotations in a way that ordinary arrows cannot capture. Spinors are the language that can capture it. This may sound abstract, but the basic reason is clear. An arrow in space is easy to rotate. Point it upward, turn it around a chosen axis, and after one complete turn it is back where it began. The arrow may have swept through space, but its final direction is the same. A spinor is more subtle. After one complete turn, it is not quite back to its original state. Something about its quantum phase has changed. Phase is a word physicists use for part of the structure of a quantum state. It is not a phase like childhood, winter, or being very interested in houseplants for a few months. It is more like the timing relationship inside a wave. A single overall phase may not be directly visible by itself, but differences in phase can matter when quantum states are compared or made to interfere. That last point is important because someone might reasonably ask, if the state changes after one full turn but no direct observation notices it by itself, why should we care? The answer is that quantum physics often reveals such changes through comparison. A lone change in phase can be hidden if there is nothing to compare it with. But if one part of a quantum system is rotated while another part is not, the difference between them can produce measurable interference. In experiments, the unusual rotation behavior of spinor states is not just a mathematical curiosity, it has observable consequences. A simple image can help, though like all images in quantum physics, it should be held lightly. Imagine 2 identical waves travelling together. If their peaks and troughs match, they reinforce. If one wave is shifted relative to the other, they may partly cancel. You do not have to see the hidden timing mark inside either wave separately. You can see the effect when the waves meet. Quantum phase works in a related way. The spinor change after one full rotation can matter when the state is compared with another state. After a second full rotation, the spinor returns fully, and the comparison changes accordingly. This is why the 720-degree fact is not nonsense. It is not saying that the electron looks different in the ordinary visual sense after one turn. It is saying that the quantum state belongs to a class of objects with a special rotation rule. Ordinary objects and arrows return after one full turn. Spinors need 2. The electron spin state is described by a spinor, and that is why its relationship to rotation is so strange. There is a well-known demonstration sometimes used to make this less impossible to imagine. Hold one end of a belt or a strip in place, then rotate the other end through one full turn. The belt becomes twisted. You cannot remove the twist without rotating back or moving through the constraint. But if you rotate through a second full turn, there is a way to move the belt around so that the twist can be undone without rotating the end back. A similar demonstration can be done with a plate held in the hand, turning the arm through 2 full rotations. After one turn, the arm is tangled. After 2, a smooth motion can restore the arrangement. This is not exactly what an electron is doing because the electron is not a belt or a plate or an arm, but the demonstration gives the mind a hint that rotations can have deeper structure than ordinary appearances suggest. Sometimes 1 full turn and 2 full turns are not equivalent when the path of rotation matters. The deep reason comes from symmetry. In physics, Symmetry is not only about a shape looking pretty or balanced, it means that some feature of nature remains consistent when we change something about our description or our viewpoint. If the laws of physics are the same after we rotate our laboratory, that is a rotational symmetry. If the same experiment works the same way today and tomorrow under the same conditions, that is connected to time symmetry. Symmetry tells us what nature does not care about. It tells us which changes leave the rules unchanged. Rotation symmetry is especially important. The universe does not seem to have a preferred left wall or right wall, a cosmic upward direction, or a special angle at which physics becomes different. If you rotate an entire experiment, the basic laws remain the same. That is why rotation is not merely a motion. It is a test of how physical things transform when our frame of reference changes. Ordinary objects transform in ordinary ways. Spinors transform in spinor ways. This is one of the places where spin becomes much deeper than the word spinning suggests. If spin were only a tiny mechanical rotation, we would expect it to behave like a small top or a little arrow. But electron spin is tied to how the electron quantum state transforms under rotations of the coordinate system, or measuring arrangement. It is about the representation of rotational symmetry in quantum mechanics. That phrase sounds formal, but its meaning can be stated more gently. Nature has rules for what it means to rotate things. Different kinds of physical objects follow different rotation rules. Electrons follow the spinor rule. The spinor rule is not visible in the same way a cup handle is visible. You cannot look at an electron and say, it has failed to return after one full turn. The electron does not present a tiny face to inspect. The effect lives in the state description and becomes meaningful in interference, magnetic behavior, and the way particles combine. That may feel less satisfying than watching a toy spin, but it is more faithful to what experiments and theory reveal. One reason this was so powerful historically is that it helped unify separate clues. Spin had been introduced to explain atomic spectra, magnetic splitting, and the two-outcome behavior of electrons. At first it could seem like an added feature, something inserted because experiments demanded it. But as quantum theory matured, spin became connected to symmetry in a deeper way. It was not merely a patch. It was part of the natural language of particles in a universe where rotation and relativity matter. The electron is a spinor particle. That means its quantum description has this special two-turn behavior under rotation. Particles like electrons, protons, neutrons and quarks belong to the fermion family, and their spinor nature is tied to the exclusion principle we have just discussed. Particles such as photons behave differently. They have their own spin, but their rotation behavior belongs to a different category. This sorting by spin is one of the basic ways particle physics organizes the world. It is not about how fast things are turning, it is about the type of quantum object they are. The word representation can be useful here if we keep it plain. A symmetry can act on different things in different ways. Rotating a chair changes its orientation in the room. Rotating an arrow changes the direction it points. Rotating a spinor changes it according to the spinor rule. The symmetry is the same general idea, rotation, but the object being rotated belongs to a different mathematical kind. This is like the way the same song can be played on a piano, a violin, or a flute. The melody is recognizably related, but each instrument expresses it differently. Rotation is the melody. Ordinary vectors and spinors are different instruments. This does not mean spinors are imaginary. They are mathematical tools, but they describe real physical behavior. Much of physics works this way. Fields are described mathematically, but electric motors run because electromagnetic fields are real in their effects. Curved space-time is described mathematically, but planets orbit and light bends because gravity behaves accordingly. Spinors are part of the mathematical description of quantum particles, and that description succeeds because it predicts measurable results. The tool is abstract. The consequences are physical. The 720-degree secret also helps show why the phrase spin up or spin down should not be treated as a little arrow story. A normal arrow does not need 2 full turns to return. A spinor does. If electron spin were simply a tiny arrow, this behaviour would make no sense. Since the behaviour is real in the quantum description, the arrow image must be limited. It can help us talk about measurement directions, but it cannot explain the structure of spin itself. There is an important caution though. When people hear that an electron needs 2 full turns to return to itself, they may imagine that after 1 turn, the electron is somehow physically upside down, or visibly altered. That is not right. The change after 1 full rotation is a change in the quantum state that may not be directly observable if it is the only change in the whole system. It becomes important through relative phase and interference. This is a subtle distinction, but it prevents a great deal of confusion. Quantum states carry information that is not always visible as a direct property in isolation, yet can still affect outcomes when states are combined. A good way to say it is this. A single full rotation changes the sign of the spinor state in the mathematical description. The word sign here is being used verbally, not as a written symbol. By itself, that overall change may not show up in a simple measurement, but relative changes of this kind can affect interference. After a second full rotation, the spinor returns completely. This is why physicists speak of the 2-turn nature of spinor particles. The connection with interference is especially important because quantum mechanics is deeply wave-like. Even particles that arrive in individual detection events can be described by states that interfere. The patterns of possible outcomes depend on how different parts of a state combine. If rotation changes the internal phase relationship, then rotation can change interference. Experiments with particles such as neutrons have demonstrated effects connected to this unusual spinor behaviour. Again, this is not a bedtime myth passed between physicists to make electrons seem mysterious. It is part of the tested structure of the theory. It is also one of the reasons quantum mechanics feels strange in a different way from classical mechanics. Classical strangeness usually comes from complexity. A storm is hard to predict because many moving parts interact. A crowd is hard to model because many people make decisions. A turbulent stream is hard because motion folds into motion. Quantum strangeness can appear even in very simple systems. A single electron spin state already carries behaviour that ordinary rotation does not match. The difficulty is not just complexity, it is a different kind of rule. Spinners show that the geometry of quantum states is richer than the geometry of ordinary objects. We live among objects that return after 1 full turn, so our intuition expects that to be universal. But intuition was trained at a scale where spinor behaviour is hidden by large numbers of particles and everyday averaging. At the quantum level, the deeper symmetry structure becomes visible. The world is not contradicting our experience. It is revealing that our experience is a special case, not the whole story. This is a useful theme to keep close. Physics does not usually say that everyday experience is false. A cup really does come back to its original appearance after 1 full turn. A wheel really does rotate. A compass needle really does point. But these everyday facts are not the final language of nature. They emerge from deeper rules. At the level of fundamental particles, those deeper rules include spinors and the 2-turn return. There is a calm humility in accepting that. The universe is not required to build itself from objects that our hands can mimic. It can have mathematical structures that only reveal themselves through careful experiments and patient theory. Spinors are one such structure. They are not decorative. They are necessary if we want to describe electrons correctly. Without them, the behaviour of spin, magnetism, atomic structure, and particle classification would not fit together in the same coherent way. This coherence matters. A good theory in physics does not merely explain one isolated fact. It connects many facts that once seemed separate. Spinors connect rotation, quantum states, magnetic behaviour, exclusion, and the nature of fermions. They help explain why electrons have the kind of spin they do, and why that spin is not a tiny physical spinning motion. The idea may be abstract, but it earns its place by bringing order to the evidence. Think back to the earlier experiments. A beam splits in a magnetic field. Spectral lines separate. Electrons require an extra two-valued label. Pauli exclusion shapes atoms. Magnets reveal collective spin behavior. At each stage, spin is present as a measured consequence. Spinners give the deeper rotational language behind these consequences. They tell us why the quantum state is not an ordinary arrow, and why the electron belongs to a special class of particles. This is also why the phrase hidden twist is helpful if we do not take it too literally. Spin is hidden because it is not a visible rotation. It is a twist in the structure of the quantum state, a twist in how the state responds to rotations and measurements. It is not hidden inside the electron as a tiny spinning gear. It is hidden in the rules that define what an electron is. That is stranger, but it is also cleaner. There is no miniature machinery to explain. There is a fundamental quantum structure to understand. The two-term behavior can feel almost playful, as if the universe has a private joke about rotation. But it is not arbitrary. It comes from the mathematical relationship between ordinary rotations and the spin-or descriptions used for particles like electrons. Ordinary rotations have a structure, and spinors live in a related structure that covers it in a deeper way. We do not need the technical details here. The important point is that one full physical rotation of the reference frame corresponds to a change in the spinor state that is not fully restored until a second full rotation. The strangeness is disciplined, it is not random. Once this is understood, the word spin becomes less misleading. It no longer tries to mean a particle turning like a planet. It points instead to a quantum property tied to rotations at the level of state transformations. An electron has spin because it is the kind of quantum object described by spinors. Its spin affects measurements, magnetism, exclusion, and matter. The 720-degree secret is one sign that this property belongs to a world deeper than everyday mechanical pictures. And yet this deeper world does not stay hidden in laboratories. Spinor behavior and spin-based rules help shape the ordinary world. They help determine what particles can be, how atoms fill, how materials respond, and how certain technologies function. The mathematics may be subtle, but the effects are all around us. Every stable atom carries the legacy of these rules. Every solid object depends on them. Every magnetic device is touched by them. There is a certain comfort in seeing that even the strangest quantum idea is not disconnected from daily life. The electron spinor may require 2 full turns in its state description, but the consequences of that strange rule help build the calm, reliable matter around you. The bed, the walls, the air, the electronics, the tissues of the body all depend on the structured behavior of particles whose quantum identities are not easy to picture. Reality is not less real because its foundation is hard to visualize. It is perhaps more remarkable because it holds together so well despite being so unlike our first images. The next natural step is to let spin leave the quiet theory room and follow it into practical life. We have seen that spin is not literal spinning, that it was discovered through experimental patterns, that it serves as a quantum label, that it explains magnetic up and down behavior, that it supports the exclusion principle, and that spinors reveal its strange relationship with rotation. Now the question becomes where this hidden property appears in the world we actually use. The answer is almost everywhere modern technology touches magnetism, measurement, and quantum control. From medical imaging machines that listen to nuclear spin, to computer memory that depends on magnetic order, to the delicate ambitions of quantum computers, spin is not only a mystery of theory, it is a working tool in the physical world. So, that hidden property becomes easier to appreciate when we stop treating it as a puzzle sealed inside theory and begin following it into the machines, materials, and measurements around us. Spin is not only a strange label in quantum mechanics, it is also something engineers use, doctors rely on, chemists measure, and physicists try to control with extraordinary care. It sits quietly behind technologies that feel completely ordinary from the outside. A hospital scanner, a computer memory device, a laboratory instrument, A quantum chip cooled near absolute stillness. Each of them may depend in some way on the fact that particles have spin, even though they are not literally spinning like tiny wheels. The most familiar example is magnetic resonance imaging, often called MRI. From the patient perspective, the experience can feel more mechanical than quantum. You lie on a narrow table, the room is cool, the machine is large, smooth, and rather serious looking. The scanner makes knocks, pulses, hums, and rhythms that sound almost industrial. It may not feel like a delicate quantum measurement, yet inside the body the machine is listening to spin. The main actors are hydrogen nuclei, which are abundant in the body because the body contains so much water and fat. Each hydrogen nucleus is a proton, and protons have spin. Because of that spin, a proton has a small magnetic character. When a person is placed inside the strong magnetic field of an imaging scanner, many of these nucleus spins tend to become slightly organized relative to the field. They do not all line up perfectly like soldiers in a parade. Human tissue is warm, restless, and full of molecular motion. But enough of a net alignment appears for the machine to work. Then the scanner sends in carefully timed radio wave pulses. These pulses disturb the nucleus spin alignment. The spins are nudged away from their settled arrangement, and as they relax back they produce faint electromagnetic signals. Those signals depend on the local environment of the nuclei. Hydrogen in fat does not behave exactly the same as hydrogen in watery tissue. Hydrogen in one kind of tissue does not relax in exactly the same way as hydrogen in another. By measuring these differences and using magnetic field gradients to locate where the signals came from, the scanner builds an image of the inside of the body. That description may sound almost practical, and that is the point. Spin is strange, but it is not useless. It gives the nuclei a magnetic handle. The machine can pull on that handle, tip it, wait for it, listen to it, and translate the response into information. The patient does not see spin. The radiologist does not see spin directly either. What appears on the screen is anatomy, shades of tissue, structures that can be interpreted by trained eyes. But underneath that image is the response of countless nuclear spins to magnetic fields and radio waves. There is something quietly astonishing about this. A property that first appeared in puzzles about atomic spectra and beam splitting now helps reveal the interior of the human body without cutting it open. The spin of a proton becomes a medical signal. The medical signal becomes a picture. The picture becomes a diagnosis, a treatment plan, or a reassurance. A quantum property crosses the distance from laboratory theory to human care. Magnetic resonance imaging grew from a broader technique known as nuclear magnetic resonance. In chemistry and physics laboratories, nuclear magnetic resonance is used to study molecules. Different atomic nuclei experience slightly different magnetic environments depending on their chemical surroundings. Because their spin behavior responds to those surroundings, scientists can use the signals to infer molecular structure. A chemist can learn how atoms are connected in a compound. A biochemist can study proteins. A materials scientist can investigate solids and liquids. Again, spin becomes a messenger. It carries information about the environment of a particle, and careful instruments learn to read that message. The phrase nuclear magnetic resonance can sound alarming because of the word nuclear, but in this context it refers to atomic nuclei, not to nuclear power or radioactivity in the usual public sense. The technique uses magnetic fields and radio waves to work with nuclear spins. The nuclei are not being split apart, they are being gently manipulated through their magnetic quantum properties. The word resonance means that the system responds strongly when driven in the right way, rather like a swing responds when pushed at the right rhythm. In magnetic resonance, that rhythm is connected to the spin and the magnetic field. This is a useful reminder that spin is not an isolated feature. It becomes powerful when combined with fields, timing, and measurement. A spin in a magnetic field has possible arrangements with different energies. Radio waves can smooth the spin system between those arrangements. Relaxation reveals how the spin returns toward equilibrium. Gradients reveal location. Computation turns signal into image. No single piece makes the whole machine. Spin is the quantum handle, but technology is the art of building a reliable instrument around that handle. Spin also lives inside magnets, including the simple magnets of daily life and the carefully engineered magnetic materials inside devices. In a permanent magnet, many microscopic magnetic contributions are organized so that their effects add rather than cancel. A large part of this behavior comes from electron spins in the material. In most substances, electron spins pair off or arrange in ways that leave no strong overall magnetization. But in materials such as iron, cobalt, nickel, and certain alloys, interactions between electrons can favor aligned arrangements over regions of the material. These regions are called domains. Where many domains align, the material becomes magnetized. A magnet sticking to a refrigerator is therefore a visible expression of quantum order. The force you feel when pulling it away is not explained by a simple picture of little spinning balls, but by the collective behavior of electron spins and electromagnetic fields in matter. The magnet does not know it is a household object. It is a material whose internal quantum states have settled into a pattern that produces a macroscopic field. That field reaches outward and interacts with other materials. What feels like a simple tug is a large-scale echo of microscopic spin alignment. The same general idea appears in data storage. For decades, magnetic storage devices use tiny regions of material whose magnetic orientation could represent information. A bit of data could be stored by arranging magnetization one way or another. Reading and writing such information depended on controlling magnetic states. Although actual devices involve many layers of engineering, material science, and electromagnetic design, electron spin is part of the foundation. Magnetism in the material comes from spin-related behavior. Information becomes physical through the arrangement of magnetic order. This brings us to spintronics, a field whose name blends spin and electronics. Traditional electronics focuses mainly on the charge of the electron. Electric currents move charge through circuits, and those moving charges carry information and power. Spintronics asks whether the electron spin can also be used as an active ingredient. Instead of using only where charge goes, devices may use how spin is oriented or how spin populations move through a material. This opens possibilities for memory, sensors, and more efficient forms of information processing. One major success connected to spintronics is the use of magnetoresistive effects, where the electrical resistance of a device changes depending on the relative magnetic arrangement of layers inside it. Such effects transformed magnetic redheads, allowing devices to detect tiny magnetic regions more sensitively. The details can become technical, but the broad principle is straightforward. Spin-dependent behavior changes how electrons move through certain materials. That change can be measured electrically. A magnetic pattern becomes an electronic signal. Modern magnetic memory technologies also draw on spin physics. In some designs, information is stored in magnetic layers, and electric currents influenced by spin can help switch or read the state. Researchers continue to study ways of moving spin information without moving much charge, or of using spin waves, which are collective disturbances in magnetic order to carry signals. Not every idea becomes a practical device, but the ambition is clear. Spin is not merely a property to observe, it may be a resource to engineer. There is a pleasing contrast here. At the start of the story, spin seemed almost impossible to picture. Now it becomes something designers try to control. They do not need to imagine a tiny ball rotating. They need to know how spin states behave in fields, materials, and interfaces. Technology often grows this way. It does not require the universe to be intuitive. It requires the rules to be reliable. Spin appears in atomic clocks as well, though different clocks use different physical transitions. Many precise timekeeping systems rely on atoms, whose internal states can be driven and measured with extraordinary stability. Some of these states involve angular momentum and spin-related structure. By locking an oscillator to a consistent atomic transition, a clock can keep time with remarkable precision. The clock is not measuring spin in the same practical sense as an imaging scanner, but the broader quantum structure of atomic states, including spin and magnetic interactions, helps create the stable reference. Timekeeping, navigation, communication, and scientific measurement all benefit from the fact that atoms have reliable internal quantum labels. In the laboratory, spin is one of the cleanest systems for exploring quantum control. An electron spin or nuclear spin can act like a small two-state quantum system. It can be prepared, manipulated, and measured. Because there are two basic outcomes when measured along a chosen direction, spin naturally invites comparison with a bit of information. But a quantum bit, or qubit, is more subtle than an ordinary bit. An ordinary bit is one of two alternatives. A qubit can be in a quantum state that combines possibilities until measurement. Spin systems can serve as qubits because their states can be controlled in quantum ways. This brings us toward quantum computing. The promise of quantum computing is not that it simply makes ordinary computers faster at everything. It is more specific and more interesting. A quantum computer uses quantum states, superposition, interference, and entanglement to process information in ways that may be powerful for certain tasks. Building such a machine is extremely difficult because quantum states are delicate. They can lose their carefully prepared character through unwanted interaction with the environment. This loss is called decoherence. To make a quantum computer work, researchers must isolate qubits enough to preserve quantum behavior while still controlling and measuring them accurately. That is not a small challenge. It is a balancing act performed at the edge of what engineering can do. Spin is one candidate for building qubits. An electron spin in a semiconductor quantum dot, for example, can represent a controllable quantum state. A quantum dot is a tiny region where an electron can be confined, somewhat like an artificial atom made inside a material. The spin of the electron can be manipulated using magnetic fields, microwave pulses, or electric control schemes depending on the design. Nuclear spins can also be used in certain systems because they may remain coherent for relatively long times. Defects in crystals, such as special imperfections in diamond, can host spin states that are controllable and readable with light. Different platforms have different strengths and weaknesses. The common theme is that spin provides a compact quantum degree of freedom. It has a two-outcome measurement structure. It can be influenced by fields, and it can be made to interact with other spins or other quantum systems. Those features make it attractive for quantum information. The difficulty is not whether spin is real enough to use. The difficulty is controlling it well enough, long enough, and in large enough numbers to perform reliable computation. A spin qubit must be protected from noise. Nearby nuclear spins, stray magnetic fields, electrical fluctuations, vibrations, heating, and imperfections in materials can all disturb the qubit. The environment is always trying, in a sense, to learn something about the quantum state. When that happens, the delicate quantum information can fade into ordinary randomness. Engineers respond with cleaner materials, colder temperatures, better shielding, error correction strategies, and clever pulse sequences that cancel unwanted effects. The work is patient and exacting. Quantum computing is not a magic box. It is a sustained effort to preserve fragile order in a noisy world. This makes spin a practical example of quantum fragility. In a magnet, many spins collectively form a robust large-scale order. In a quantum computer, an individual spin state may need to remain delicate and coherent. The same general property can appear as sturdy magnetism in one context and as fragile quantum information in another. What matters is the system, the environment, and the way the spin is used. Spin also appears in quantum sensing. Because spin states can be sensitive to magnetic fields, electric fields, temperature, strain, and other local conditions, they can serve as tiny probes. Some diamond-based spin systems, for instance, can detect very weak magnetic fields at small scales. Researchers investigate these systems for imaging materials, studying biological samples, and probing nanoscale environments. The idea is elegant. A controllable quantum spin becomes a sensor, reporting on the world around it through changes in its state. This is another shift from mystery to tool. The same odd feature that once confused physicists because it was not literal rotation becomes a practical measuring device. Spin is not only something to explain, it is something to ask questions with. Place it near a sample, control it carefully, watch how it changes, and it can reveal hidden fields or structures. Particle physics also uses spin as a basic identifier. When physicists classify particles, spin is one of the first properties they name, alongside mass, charge, and other quantum features. The spin of a particle helps determine what kind of particle it is, how it behaves collectively, and what interactions are possible. The distinction between matter particles and force-carrying particles is tied to spin families. This classification is not cosmetic. It is part of the deep grammar of the standard model of particle physics. Light itself carries spin. Photons, the particles of light, have spin related to polarization. Polarization describes the orientation behavior of light waves, and it has many practical uses. Polarized sunglasses reduce glare by filtering light with certain polarization properties. Liquid crystal displays use polarization to control brightness and color. Optical communication systems can use polarization in sophisticated ways. Once again, a spin-related quantum property reaches ordinary technology. The effects may be described in wave language for many purposes, but at the quantum level, photons carry angular momentum connected to their spin. There are also devices that use the spin of electrons to study materials through electron spin resonance. This technique is related in spirit to nuclear magnetic resonance, but it focuses on unpaired electron spins. Because unpaired electrons are sensitive to their local environment, electron spin resonance can reveal information about radicals, defects, transition metal ions, and other systems. Chemists, physicists, and biologists use it to investigate materials and reactions. An unpaired spin becomes a signature of structure and environment. The recurring pattern is clear. Spin gives particles a magnetic and angular quantum property. Fields can interact with it, measurements can detect it, materials can organize it, technologies can exploit it. From medicine to memory, from spectroscopy to quantum sensing, spin is woven into practical science. This does not make spin less mysterious. It makes the mystery more trustworthy. We are sometimes tempted to think that only picturable things can be used, but modern technology proves otherwise. Engineers routinely build devices on principles no human can visualize in the simple everyday way. Semiconductor electronics depend on quantum band structure. Lasers depend on stimulated emission and quantum states of light and matter. Magnetic resonance depends on nuclear spin. Quantum computers may depend on carefully controlled superpositions of spin states. The world does not have to be easy to imagine in order to be reliable enough to use. There is a quiet lesson here about understanding. To understand spin does not mean turning it into a tiny spinning object. It means knowing how it behaves, how it is measured, how it couples to magnetic fields, how it contributes to matter, and how it can be controlled. Understanding is not always a picture. Sometimes it is a network of dependable relationships. Spin is real because that network works. It predicts the beam splitting, the atomic spectra, the magnetic material, the scanner signal, and the qubit manipulation. A person in an MRI scanner does not need to know quantum mechanics for the machine to work. A computer user does not need to know spintronics for data to be read. A patient benefiting from an image does not need to picture proton spin. Technology often hides its deepest ideas beneath smooth surfaces and simple buttons. But beneath those surfaces, the quantum world continues to operate with quiet precision. This is one reason physics can feel so rewarding. It reveals that everyday objects are not as plain as they seem. The hospital scanner is not only a machine, it is a conversation with nuclear spin. A magnet is not only a useful object on a refrigerator, it is a collective quantum arrangement. A data device is not only an electrical tool, it may be reading microscopic magnetic states. A quantum computer prototype is not only a cold chip in a laboratory, it is an attempt to make individual quantum states carry and process information without losing their delicate coherence. Spin, then, is not an obscure label trapped in textbooks. It is a working feature of matter and radiation. It helps scientists see inside the body, identify molecules, design materials, store information, measure tiny fields, and explore new forms of computation. It is both fundamental and useful, both strange and practical. The fact that particles do not literally spin makes the story more interesting, not less. If spin were just ordinary rotation, it would be easier to picture, but it would not explain the full quantum structure we observe. Its usefulness comes precisely from its true nature as an intrinsic quantum property. As these real-world examples gather together, the original question begins to change shape. We started with a puzzle about a misleading word. If particles do not spin, why do they have spin? We found that the word points toward angular and magnetic behaviour, but not toward a tiny rotating surface. We followed spin through experiments, quantum labels, magnetic measurements, exclusion, spinners, and now technology. The same idea has appeared in many forms, each one showing a different face. Spin is a measurement outcome, an intrinsic property, a magnetic handle, a symmetry behaviour, a classification label, and a practical tool. The final step is to gather these faces without forcing them into a false simplicity. Spin is not one of those ideas that becomes completely ordinary once explained. It remains quantum. It remains unlike a wheel or a planet. But it can become familiar in another way, the way a person becomes familiar not because we can reduce them to one sentence, but because we have seen them in different situations and recognize the pattern of who they are. Spin is recognized by its effects. It is what makes beams split, atoms arrange, magnets hold, scanners listen, and qubits tremble between possibility and measurement. To ask what spin really is, then, is not to search for a tiny hidden mechanism, but to understand the role this property plays in the grammar of the physical world. To ask what spin really is, after all of this, is to stand at the edge of a very old habit of the human mind. We want the hidden thing behind the word. We want the little mechanism. We want to lift the cover from the clock and find gears turning in a way that explains the ticking. With ordinary machines, this instinct often serves us well. A door opens because hinges rotate. A kettle whistles because steam escapes. A bicycle moves because wheels turn and chains pull. We learn the world by finding motions inside other motions, but spin asks us to be careful. It has a name that sounds mechanical, yet it belongs to a level of nature where our familiar mechanical pictures no longer give the final explanation. So what is spin, really? It is an intrinsic quantum property of particles. That is the shortest honest answer, but it is not yet a satisfying one, so we need to unfold it patiently. Intrinsic means the property belongs to the particle as part of what it is. An electron does not gain spin because it is circling a nucleus. It does not lose spin because it is alone. It does not spin faster when pushed in the way a wheel might spin faster. Every electron has the same kind of spin because having that spin is part of being an electron. In the same way, an electron has electric charge and mass, not because it is performing some hidden trick, but because those properties define its physical identity. Spin belongs in that same deep category. Quantum means the property follows the rules of the small world, not the rules of familiar objects moving through daily life. A spinning tennis ball has a surface, a size, a rotation rate, and parts that move around an axis. An electron, as far as experiments can tell, does not offer us that kind of extended structure. There is no tiny painted dot to watch as it goes around. There is no little crust sliding through space. There is no wheel rim whose speed we can calculate with ordinary imagination. And still, the electron has a property that behaves in ways related to angular momentum, magnetism, and rotation. That property is spin. This is why spin is not a fake idea, even though the name can mislead. It is not a metaphor physicists use because they cannot think of anything better. It is measurable. It changes experimental results. It explains why beams split in magnetic fields, why atomic spectral lines have fine structure, why electrons fill atoms in layered patterns, why many materials are magnetic or not magnetic, why some medical machines can image the body, and why quantum engineers can imagine using individual particles as carriers of information. Spin is not something we see directly. It is something we know through its effects, and in physics, effects are often how reality introduces itself. A calm way to hold the idea is this: spin is the built-in angular character of a quantum particle. The word angular matters because spin is related to rotations and magnetic behavior. The word built-in matters because it is not caused by ordinary motion. The word quantum matters because its rules are not the rules of a tiny classical top. Put together, they give us a useful sentence. Spin is a built-in quantum form of angular momentum. But even that sentence should be held gently, because it tells us what family of properties spin belongs to, not that it is ordinary rotation in disguise. When physicists measure electrons spin along a chosen direction, they get one of two possible outcomes. They often call these outcomes spin up and spin down. These names are practical, but they can be sneaky. Up and down do not mean that the electron carries a tiny arrow pointing toward the ceiling or the floor in the everyday sense. The measuring device defines the direction of the question. The electron state answers that question with one of two allowed results. If the apparatus is turned, the question changes. The answers remain quantum answers, not the revelation of a simple little hidden compass needle. This is one of the most important lessons spin teaches. Quantum measurement is not always the same as looking at a pre-existing ordinary property. If you check whether a book is on a table, you are usually revealing something that was already true in the everyday sense. But when you measure the spin of an electron along a direction, the quantum state and the measurement interaction are bound together in a more subtle way. The result is definite once measured, but before measurement the state may not correspond to a tiny object with all directions already settled like a classical arrow. This does not make spin unreal. It means the reality described by quantum mechanics is not simply a hidden version of the everyday picture. Spin is also tied to symmetry. This may sound like a step away from physical reality, but symmetry is one of the deepest ways physics understands the world. A symmetry tells us what remains consistent when something is changed. Rotate a whole experiment, and the laws of physics remain the same. That consistency is not trivial. It means the universe has no preferred direction built into its basic rules. Spin tells us how a particle state behaves under such rotations. Particles like electrons are described by spinors, which have a strange two-turn character. An ordinary object returns to its starting appearance after one complete turn. The spinor state of an electron returns fully only after a second complete turn. This is not because the electron is a tiny dancer rotating twice. It is because the quantum state follows a deeper rule for rotations. That two-turn behavior is one of the clearest signs that spin is not an ordinary mechanical motion. No everyday arrow needs that kind of return. A chair, a cup, a wheel, and a planet all fit the common rotation picture. Spinors do not. The electron belongs to a different mathematical and physical category. The word mathematical here should not make the idea seem less real. The mathematics of spin works because nature behaves that way. It predicts what experiments reveal. It connects the magnetic behavior of particles, the structure of atoms, and the classification of matter. A description that keeps succeeding is not merely decoration. It is part of how physics speaks accurately about the world. Spin also explains why particles can be sorted into families with very different collective behavior. Electrons are fermions. Fermions obey the Pauli exclusion principle, which says that no two identical fermions can occupy the exact same quantum state. This rule is one of the reasons atoms have structure. Electrons fill states in layers because they cannot all pile into the lowest one. Spin is part of the quantum address that distinguishes one electron state from another. Because of spin, two electrons can share the same spatial orbital state, only if their spin labels differ. Once those possibilities are filled, other electrons must occupy different states. From this comes the architecture of shells, and from shells comes much of chemistry. This makes spin part of the answer to an unexpectedly large question. Why is matter not all the same? Why do atoms have different personalities? Why does carbon make so many bonds while neon remains aloof? Why does iron behave differently from oxygen, and sodium differently from chlorine? The number of protons in the nucleus defines the element, but the arrangement of electrons gives each element much of its chemical behaviour. That arrangement depends on quantum numbers, spin, and exclusion. A hidden property of particles helps write the periodic table. Spin is also part of why matter takes up space. The firmness of a table or a wall is not explained by atoms as tiny hard marbles packed against one another. Atoms are mostly structured fields and electron states. When matter is pushed into matter, electron states resist being forced into forbidden arrangements. Electromagnetic repulsion is important, and so is the exclusion principle. Together they create the contact forces we feel. Your hand does not pass through a table because the quantum structure of matter does not permit effortless overlap. Spin contributes to the rules behind that structure. Something that cannot be pictured as a little spinning surface helps make surfaces feel solid. In magnets, spin becomes almost visible through collective behaviour. A single electron spin is microscopic and quantum, but when many electron spins in a material organise in a common pattern, the result can be a magnetic field large enough to hold a note to a refrigerator. Most materials do not become strong permanent magnets because their electron spin effects cancel or remain disordered. In certain materials, however, the spins can cooperate. Small regions align. Those regions can align with one another. The hidden quantum property becomes a familiar everyday force. You pull a magnet from the fridge, and in that small resistance is a trace of quantum order. In magnetic resonance imaging, spin becomes a tool for seeing inside the body. Hydrogen nuclei have spin. In a strong magnetic field, their spin behaviour can be influenced by radio waves. As the nuclei relax back, they produce signals that reveal information about the tissues around them. A computer turns those signals into images. The patient experiences a large machine, a table, and a series of knocks and hums. Beneath that experience, the machine is working with spin. A property of nuclei becomes a medical picture. The invisible becomes diagnostic. In quantum computing, spin becomes a possible carrier of information. A spin state can act as a quantum bit, able to be prepared, controlled, and measured. It can participate in superposition and entanglement, the delicate features that make quantum information different from ordinary information. Building reliable quantum computers is extremely difficult, because quantum states are easily disturbed by their surroundings. But spin remains attractive because it is compact, controllable, and deeply quantum. The same property that confused early physicists now sits at the centre of some of the most advanced technological ambitions of our time. So what is spin? Really? It is not a tiny rotating ball. It is not a little arrow hidden inside a particle. It is not a surface motion, not a miniature planet, not a bead whirling faster than light. It is a fundamental quantum property that behaves like angular momentum, responds to magnetic fields, determines possible measurement outcomes, shapes how particles combine, and reflects the deeper symmetry rules of the universe. That may sound like several answers rather than one, but perhaps that is because spin does several kinds of work. It is a property of individual particles. It is a label in quantum states. It is a source of magnetic behaviour. It is tied to the exclusion principle for matter particles. It is described by spinors, It can be used in machines. It is a real feature of the world, known not through a simple picture, but through a network of consequences. Trying to reduce spin to one everyday image would make it easier to imagine and less true. There is no shame in wanting the image. Human understanding often begins with pictures. The atom as a tiny solar system, light as a wave, electrons as little balls, spin as rotation. Each picture helps for a while. Then experiments ask for more. The solar system atom fails. Light becomes both wave-like and particle-like depending on how we ask. Electrons stop being little balls. Spin stops being literal spinning. Science does not destroy the earlier image out of cruelty. It outgrows it because the world contains more than the image can hold. In that sense, spin is a lesson in intellectual gentleness. We begin with a familiar word. We let it guide us, but not trap us. We keep what is useful and release what is false. Spin keeps the connection to angular behavior, but releases the tiny top. It keeps the connection to magnetism, but releases the little bar magnet. It keeps the language of up and down, but releases the fixed hidden arrow. What remains is stranger, clearer and more powerful. This is also why quantum physics does not have to be treated as a collection of impossible riddles. It is strange, yes, but it is not arbitrary. Spin has rules, it has measurements, it has consequences. It connects to experiments and technologies. The difficulty lies not in the universe being nonsense, but in the universe being organized according to principles that our everyday instincts did not anticipate. Once we stop demanding that every particle behave like a tiny familiar object, the pattern becomes easier to respect. A useful final way to think about spin is to call it a kind of quantum identity. Particles are not only distinguished by where they are or how they move, they are distinguished by properties that define how they can exist, interact, and combine. Spin is one of those defining properties. It tells us something about what kind of particle we are dealing with and how that particle belongs to the larger order of nature. The electron has its spin, the photon has its spin, other particles have theirs. These differences are not cosmetic. They shape matter, light, forces, and the possible structures of the universe. And because spin is part of identity, it is present even when no one is measuring it. Measurement reveals outcomes, but the property is built into the particle description. An electron is not waiting to become a spin-carrying object only when a physicist enters the room. It is the kind of quantum object for which spin is part of the theory, part of the behavior, part of every accurate account we have. The measurement gives a particular answer along a chosen direction, but the existence of spin as a property is not invented by the moment of looking. This distinction is subtle but important. We should not imagine a simple hidden arrow, yet we also should not imagine spin as merely a word for our ignorance. It is neither a classical object inside the particle nor a human fiction. It is a quantum property. That middle ground is where much of modern physics lives. Reality is not always classical, but it is still reality. As the journey through spin settles into one piece, the original puzzle softens. If particles do not spin, why do they have spin? Because spin is not the motion the word first suggests. It is a name for an intrinsic quantum property with angular and magnetic character. The name came from resemblance to rotation, but the property itself belongs to the deeper structure of quantum theory. Particles have spin because the universe includes quantum objects whose states transform in these spin-dependent ways, whose measurements yield these discrete outcomes, and whose collective behavior builds the matter and technology around us. The electron does not need to be a tiny spinning planet to help make atoms stable. It does not need a surface to respond to a magnetic field. It does not need a little axle to obey the rules of spinors. It does not need to match a bedtime picture in order to be real. It only needs to behave consistently, and it does. Again and again, experiment finds the marks of spin. Again and again, theory shows how spin belongs to the structure of particles. Again and again, technology proves that the property can be used. So, after all the strange turns, perhaps the simplest honest answer is this. Spin is what rotation becomes when nature is quantum. Not rotation as a wheel performs it, not rotation as a planet displays it, but rotation translated into the language of particles, states, symmetries, and measurement. It is the quantum shadow of angular behaviour, though even shadow is only an image. It is a property that cannot be held, cannot be seen directly, and cannot be reduced to a tiny motion, yet it helps hold the visible world together. And now, here we are, a little farther along in our own quiet path through the subject. We began with a word that seemed familiar, and found that it opened into magnets, atoms, matter, medical imaging, quantum information, and the strange two-turn behaviour of spinners. All from a word that sounds like a toy top on a table. That is often how physics rewards patience. A small question turns out to contain a whole landscape. If this journey has made the world feel a little stranger, that is not a bad thing. Strange does not mean distant. The strangeness of spin is inside the matter around you, inside the chemistry of your body, inside the devices near you, and in the light moving quietly through the room. It is not separate from ordinary life. It is one of the reasons ordinary life can have its shape. So as the thought begins to loosen and the edges of the day soften, let the idea rest without needing to be forced into a picture. The electron is not a little spinning ball. The proton is not a tiny wheel. The quantum world is not a miniature version of the visible one. It is deeper, stricter, and more surprising. Spin is one of its signatures, a quiet built-in property that reveals itself through magnets, spectra, atoms, and machines, and it is not what the word first promises, but it is something better. It is a reminder that reality can be understandable without being ordinary. And if this calm little walk through the hidden twist of particles has kept you company, helped your thoughts slow down, or made the universe feel gently larger before sleep, I would be grateful if you liked the video, subscribed, or shared it with someone who enjoys science at a softer pace. For now, there is nothing more you need to solve. The particles may keep their spin, the atoms may keep their structure, the magnets may keep their quiet hold, and the night may keep unfolding at its own patient speed. Rest well, fellow traveller, wherever you are, and let the small unseen rules of the universe carry on without needing you to watch them too closely.